At this very moment, there are more stars in the universe than there are grains of sand on all the beaches on Earth. Recent discoveries shed light on enigmatic phenomena that challenge established theories, raising questions about our place in this enormous arena. From the nature of dark matter and dark energy to the intricate fabric of space-time, join us as we delve into everything we don't know about our universe. Dark matter remains one of the most intriguing mysteries in cosmology. Although it is believed to constitute nearly 27% of the universe, its exact nature eludes scientists. One of the greatest questions revolves around what dark matter is made of. There are several candidates, such as weakly interacting massive particles and axions, but no conclusive evidence has confirmed any of these theories. Another major question is how dark matter influences the formation of galaxies. Observations reveal that galaxies rotate at speeds that should cause them to fly apart. The presence of dark matter helps explain these dynamics, but researchers are still trying to understand this force better. Why does it clump in particular ways, influencing the large-scale structure of the universe while appearing imperceptible at a smaller scale? Furthermore, scientists are puzzled by the interactions of dark matter with ordinary matter, if any exist at all. Most theories suggest that dark matter interacts very weakly with itself and with normal matter, which makes it extremely difficult to detect. Researchers are exploring ways to observe these rare interactions, hoping to unlock further secrets about this elusive substance. Lastly, there is an ongoing debate about dark energy's relationship with dark matter. While dark matter pulls things together, dark energy seems to push things apart, accelerating the expansion of the universe. Understanding how these two forces coexist and interact is fundamental to grasping the universe's overarching dynamics. As scientists continue to probe these questions, the mystery of dark matter deepens, inviting further exploration into the universe's fabric. Scientists define dark energy as a mysterious force that permeates all of space and is responsible for the accelerating expansion of the universe. Its existence was suggested in the late 20th century when observations of distant supernova revealed that the universe's expansion is not slowing down, as previously thought, but rather speeding up. This surprising behavior indicated that some kind of energy, distinct from matter and radiation, must be pushing galaxies apart. Dark energy is estimated to constitute roughly 70% of the total energy density of the universe, making it a dominant component in cosmological models. To search for dark energy, scientists employ various techniques and observational tools. One of the most prominent methods includes studying supernovae, specifically type Ia supernovae, which serve as standard candles for measuring cosmic distances. By comparing the brightness of these explosions at various distances, researchers can assess how the expansion of the universe changes over time. Galaxy clusters, gravitational lensing, and measurements of the cosmic microwave background are also vital in gauging the effects of dark energy. These methods combine to provide a clearer picture of how dark energy influences the cosmos. Understanding dark energy is crucial because it fundamentally alters our comprehension of the universe's fate. If dark energy continues to dominate, the universe may face an endless expansion, leading to a scenario known as the Big Freeze. Conversely, if properties of dark energy were to change, different outcomes such as a big crunch could arise. Such possibilities raise profound questions about the nature of space-time, the ultimate destiny of celestial bodies, and the very fabric of reality itself. As scientists delve deeper into the nature of dark energy through advanced techniques and theoretical innovations, each discovery could provide a clearer insight into this enigmatic force. The quest for knowledge about dark energy not only illuminates the conditions that shaped our universe, but also unveils the mysteries that still lie ahead, shaping our understanding of existence itself. The phenomenon of missing baryons refers to a discrepancy between the amount of ordinary matter we expect to find in the universe and the amount that we can actually observe. According to our current understanding, baryons, which are particles making up protons and neutrons, constitute about 5% of the total energy density of the universe. However, surveys conducted across different wavelengths have revealed that we can account for only a portion of this expected baryonic matter. The remainder appears to be elusive, leading scientists to ponder its fate. One significant implication of these missing baryons is their potential distribution in the vast intergalactic medium. Cosmological simulations suggest that this undetected matter might exist in a diffuse state, spread thinly throughout the space between galaxies, possibly in forms such as warm or hot gas. If these baryons were indeed residing in this unseen form, it could entirely reshape our understanding of cosmic structure formation and the evolution of the universe. The existence of these missing baryons might also suggest that our current models significantly underestimate the complexities of cosmic processes. For instance, the interplay between baryons and dark matter during the formation of galaxies could undergo re-evaluation. This would mean rethinking how galaxies like our Milky Way emerged from primeval gas clouds, which is vital for deciphering the history of our cosmos. Furthermore, the search for the missing baryons is a quest that may bridge gaps between different fields of astrophysics. Discovering and characterizing this matter could provide insights not only into cosmic structure, but also into fundamental questions about the nature of matter and energy in the universe. Thus, the exploration of missing baryons stands as a pivotal chapter in our quest to understand the full tapestry of reality in which we reside. Cosmic voids are vast, empty spaces in the universe that contain very few galaxies compared to other regions. These voids can stretch for millions of light years and are essential in shaping the large-scale structure of the cosmos. Their existence helps define the cosmic web, a sprawling structure made up of dense clusters of galaxies interconnected by filaments of dark matter, with the voids acting as the empty gaps between these dense areas. The influence of cosmic voids on the universe's evolution is significant. As the universe expands, voids may grow larger and become even sparser. This expansion leads to a lower density of matter in these regions, allowing dark energy's effects to dominate. This causes a distinct evolution in the structures found within and around voids. Galaxies situated at the edges of these voids often experience different gravitational influences compared to those situated within denser clusters. Interestingly, the dynamics of voids can also affect galaxy formation. In less dense regions, galaxies tend to form later than in denser areas, often resulting in differences in their characteristics. Galaxies within voids may be smaller and have fewer stars due to their delayed formation and the lack of available material to build upon. This highlights an intriguing aspect of cosmic evolution. Voids are not merely empty spaces, but rather dynamic regions with their own unique processes shaping the universe. Research into cosmic voids also offers insights into the nature of dark matter and dark energy. By studying how voids interact with surrounding structures and how they influence the movement and clustering of galaxies, scientists gather valuable information about the underlying mechanisms of the universe. This understanding is key in piecing together the broader puzzle of cosmic evolution and the fundamental forces at play. The Fermi paradox presents a compelling contradiction within our search for extraterrestrial life. Named after the physicist Enrico Fermi, the paradox arises from the expectation that, given the vastness of the universe and the high likelihood of Earth-like planets, we should already have evidence of alien civilizations. Yet, the absence of such evidence prompts a deeper exploration of our place in the cosmos and our assumptions about life beyond Earth. One implication of the Fermi paradox is the possibility that intelligent life is exceedingly rare. Even in a universe containing billions of galaxies, each with millions or even billions of stars, we might be among the few advanced species. This challenges our understanding of the conditions necessary for life to evolve into an intelligent form. It suggests that complex life could be a unique occurrence, or that planetary environments may frequently inhibit the development of intelligent civilizations. Another perspective raised by the Fermi paradox relates to the self-destruction of civilizations. It is possible that advanced societies tend to develop technologies capable of causing their own demise before they can explore the stars or communicate with others. This notion points to a critical need for understanding the sustainability of technological advancement as it pertains to the long-term survival of a species. The challenges faced by humanity may mirror those confronting other potentially intelligent beings throughout the universe. Moreover, the paradox invites speculation about the nature of extraterrestrial civilizations. They might be engaging in forms of communication that we cannot comprehend, or they could be intentionally avoiding us. Some theories even suggest that advanced alien cultures may have chosen to remain silent or hidden, observing us without revealing their presence, akin to a cosmic prime directive. Each of these ideas adds layers to our quest for knowledge about life beyond Earth and reinforces the significance of searching for answers in both the vast cosmos and within ourselves. Scientists have gathered compelling evidence indicating that the universe is not just expanding, but doing so at an accelerating rate. This pivotal discovery stemmed from observations of distant supernovae during the late 1990s. When astronomers studied these explosive events, they found that the light from the farthest supernovae was dimmer than expected. This indicated that they were farther away than previously thought, suggesting that the expansion of the universe is hastening. This acceleration is attributed to a mysterious force termed dark energy, which is believed to comprise about 70% of the total energy content of the universe. Dark energy is a theoretical concept that was introduced to explain the observed acceleration, even though its exact nature remains elusive. Unlike gravity, which pulls matter together, dark energy appears to exert a repulsive force that counteracts gravity's influence on galactic scales. Alongside this, scientists have been able to measure the cosmic microwave background radiation, the afterglow of the Big Bang, which provides additional support for the universe's expansion and its accelerated nature. These measurements help describe the universe's composition and dynamics over cosmic time. They serve as a valuable tool in understanding how different forces at play contribute to the universe's fate. Astrophysical models and simulations continue to evolve as researchers seek a deeper understanding of dark energy and its role in cosmic expansion. The notion that our universe is expanding ever more rapidly opens up fascinating questions about its ultimate fate. Will this acceleration continue indefinitely, leading to a fragmented cosmos, or will other forces eventually intervene? The mysteries of the universe persist, leading humanity to explore its vastness further. The edges of our universe harbor various mysterious phenomena that continue to intrigue scientists and challenge our current understanding of cosmology. One of the most perplexing aspects is the concept of cosmic voids, which are enormous, empty regions of space that contain very few galaxies. These voids disrupt the uniform distribution of matter we expect in the universe and raise important questions about the overall structure and evolution of cosmic matter. Another enigmatic phenomenon is the accelerated expansion of the universe, a process driven by what we call dark energy. While dark energy is believed to comprise a significant portion of the universe, its true nature remains elusive. This expansion is causing galaxies to move away from us at increasing speeds, suggesting that the fabric of space itself is stretching. The realization that the universe may be expanding faster than previously thought leaves many scientists scratching their heads as they seek to understand the underlying principles governing these forces. Additionally, the cosmic microwave background radiation, which is the faint afterglow of the Big Bang, presents its own set of puzzles. This radiation appears remarkably uniform across the sky, with slight fluctuations that point to the early universe's density variations. However, certain anomalies have been observed in these variations that some researchers argue could indicate regions beyond our observable universe, or even alternate physical laws governing those areas. Finally, there is the intriguing concept of the multiverse, which posits that our universe may be just one of many. This idea raises a multitude of questions about the fundamental nature of reality and what it means for our understanding of space and time. While the multiverse theory remains speculative, it forces scientists to confront the limits of our observational capability and challenges the boundaries of established scientific thought. Each of these phenomena fuels ongoing research and inquiry, pushing us to explore the very foundations of our knowledge about the cosmos. Gravitational waves are ripples in the fabric of spacetime that occur when massive objects like black holes collide or orbit one another. These waves travel across the universe at the speed of light and carry important information about the events that produced them. The detection of these waves marks a significant advancement in our ability to observe the cosmos, allowing us to study phenomena that would otherwise remain hidden from sight. When two black holes merge, the gravitational waves generated weave through space and can be detected by instruments such as the Laser Interferometer Gravitational Wave Observatory. When scientists first detected gravitational waves in 2015, it was a groundbreaking moment that confirmed predictions made by Albert Einstein's general theory of relativity. Each wave encodes details about the masses of the black holes involved, their distance from Earth, and even the energy released during the merger. By analyzing these signals, researchers can gather evidence about the properties of black holes, such as their spin and size, which were previously elusive, trapped behind the black hole's event horizons. Furthermore, gravitational waves challenge and refine our understanding of spacetime itself. They provide direct evidence of how mass influences the curvature of space, a core concept in general relativity. This insight prompts scientists to explore deeper questions about the universe's most enigmatic phenomena, such as the true nature of black holes and their role in cosmic evolution. The ability to hear the universe through gravitational waves opens new frontiers in astrophysics and reveals the dynamic processes occurring across the cosmos. As further detections continue, researchers hope to observe a variety of events not only involving black holes, but also neutron stars and potentially other exotic cosmic occurrences. This burgeoning field of gravitational wave astronomy will undoubtedly enhance our comprehension of the universe, offering a novel perspective on the fundamental fabric of reality and the interactions that shape it. Fast radio bursts are incredibly brief, but powerful bursts of radio waves that last only a few milliseconds. Discovered in 2007, these enigmatic phenomena can release energy equivalent to that of the sun's output over several days, all in the blink of an eye. The precise origin of fast radio bursts remains a mystery, drawing researchers from various fields of astrophysics to investigate their potential sources, which could range from collapsing stars to more exotic possibilities like merging black holes or magnetic neutron stars. Despite extensive observations and the advent of advanced detection technologies, we still grapple with several unanswered questions about these bursts. Notably, their rate of occurrence suggests there may be tens of millions of these events happening throughout the universe every day. Yet, pinpointing their exact locations remains a challenge. Most bursts are detected as one-off events, and only a handful have been observed to repeat, complicating our understanding of their origins. This unpredictability has hindered efforts to study them in greater detail. Another area of confusion involves how these bursts interact with their surroundings. As they travel across vast cosmic distances, fast radio bursts can be influenced by the intervening material of the universe, which alters their properties. Understanding this influence is crucial, as it may shed light on the density and distribution of matter in the universe, including dark matter, which constitutes a significant portion of the cosmos yet remains poorly understood. As we advance our technologies and undertake deeper observations, fast radio bursts could unlock new insights into the violent and energetic processes occurring across the cosmos. Each discovery pushes us closer to understanding not only the nature of these bursts, but also the fundamental mechanisms driving the universe's evolution, making them an invaluable focal point for ongoing astronomical research. The concept of the multiverse presents a fascinating challenge to traditional scientific paradigms by suggesting that our universe is just one of potentially countless others. This idea diverges from the classical perspective that posits a single observable universe governed by uniform laws of physics. Instead, the multiverse theory proposes various universes, each possibly possessing its own distinct laws, constants, and conditions. This notion opens up an array of possibilities that fundamentally alters our understanding of reality. One of the most stimulating aspects of the multiverse theory is how it reinterprets the nature of existence. If there are indeed infinite variations of universes, it implies that every possible outcome of any event might be realized somewhere within this vast array. This challenges the established scientific method, which relies on observation and experimentation to validate theories. The multiverse concept often lies beyond the reach of direct testing, leading to debates about its scientific legitimacy. Critics argue that if we cannot observe or measure these other universes, then the theory might lean more toward philosophical speculation than empirical science. Furthermore, the multiverse challenges the uniqueness of our own universe. It raises essential questions about the conditions of our existence and why we find ourselves in this particular universe. For example, why are the physical constants we observe finely tuned to allow for the existence of life? The multiverse theory suggests that if many universes exist, it is not particularly surprising that at least one would have the right conditions for life as we know it. This concept is intriguing but also leads to difficult philosophical implications regarding our place in the cosmos. As we continue to explore the implications of the multiverse, the dialogue between cosmology and philosophy becomes increasingly important. Discussions surrounding the multiverse encourage an examination of what constitutes evidence and how we define reality. Ultimately, this groundbreaking concept invites us to rethink our approach to science as well as the fundamental nature of existence, keeping the pursuit of knowledge vibrant and continually evolving. Recent discoveries regarding exoplanets have significantly advanced our understanding of which worlds might support life. One of the most exciting developments is the identification of planets located within their star's habitable zone, a region where conditions could allow liquid water to exist. A notable example is the discovery of a planet called Proxima Centauri b, which orbits a star only 4.2 light-years away. This proximity allows for more detailed observational studies regarding its atmospheric composition. Another fascinating finding involves the detection of various molecular signatures in the atmospheres of certain exoplanets. Using high-powered telescopes, astronomers have identified gases such as water vapor, methane, and carbon dioxide, which are key indicators of potential biological processes. The presence of these molecules hints at the possibility of life, especially when found in conjunction with conditions conducive to habitability. Moreover, astronomers are now exploring a concept known as superhabitable worlds. While our template for habitability mainly revolves around Earth-like conditions, these researchers propose that there could be worlds that are even more favorable for life, featuring stable climates, abundant resources, and diverse ecosystems. This shift in perspective invites imaginative exploration of what life might be like in environments different from our own. The Kepler Space Telescope and its successors have contributed immensely to this field. So far, thousands of exoplanets have been catalogued, many of which are similar in size and temperature to Earth. These discoveries kindle the hope that we may soon find concrete evidence of life beyond our planetary system. As our technologies improve, the search for signs of extraterrestrial life continues to evolve, bringing us closer than ever to answering one of humanity's greatest questions. The discovery of water on Mars significantly altered our understanding of the planet's potential to support life. For many years, scientists have debated whether Mars ever had conditions suitable for life as we know it. The detection of water, especially in the form of ice and salty liquid brines, suggests that there may be environments where microbial life could exist, or even exist in the past. Evidence from missions like the Mars Reconnaissance Orbiter has shown signs of recurring slope lineae, dark streaks that appear to flow during warmer seasons, thought to be related to briny water. These findings hint at the presence of liquid water in certain conditions, thereby increasing the chances of finding life. The existence of water also raises the possibility of former, more temperate climates on Mars, one where life could have arisen. Moreover, researchers are now investigating extreme environments on Earth, such as Antarctica and deep-sea hydrothermal vents, where life thrives in harsh conditions. These studies give hope that if life could adapt to such extremes here, it may have similarly survived on Mars. The discovery of water means Mars is not just a dry, barren world, but potentially a dynamic environment where life might have thrived. As scientists continue to explore Mars with rovers and landers, they are not only searching for signs of past life, but also studying how water shaped Martian geology and climate. This evolving understanding propels the quest for definitive proof of life beyond Earth, making Mars one of the most intriguing targets in our search for extraterrestrial organisms. The cosmic microwave background radiation is a faint glow that fills the universe and is a remnant from the early stages of cosmic history, specifically from about 380,000 years after the Big Bang. One of the most groundbreaking findings from the study of this radiation is that it provides a snapshot of the universe at a critical moment in its evolution. By analyzing the slight variations in temperature across the background radiation, scientists have gained invaluable insights into the density fluctuations that would ultimately lead to the formation of galaxies and large-scale structures in the universe. These temperature fluctuations reveal crucial information about the universe's composition. The cosmic microwave background has confirmed the existence of dark matter and indicated that ordinary matter, which makes up stars and planets, constitutes only a small fraction of the total mass-energy content of the universe. Additionally, data from this radiation has pointed to the existence of dark energy, a mysterious force responsible for the accelerated expansion of the universe, which significantly shapes our understanding of cosmic evolution. Another compelling revelation from studying the cosmic microwave background is the estimation of the universe's age. Observations suggest that the universe is approximately 13.8 billion years old, allowing scientists to refine their models of cosmic history. These measurements have not only enhanced our understanding of how the universe began, but also underscore the intricate relationship between space, time, and the fundamental forces of nature. Moreover, the cosmic microwave background serves as a key piece of evidence supporting the Big Bang theory. The uniformity of this radiation, with minor fluctuations, corresponds to the predictions made by this theory, further validating it as the leading explanation for the origin of the universe. As scientists continue to explore the cosmic microwave background with more advanced technology, they are likely to uncover even deeper truths about the very fabric of the cosmos. The launch of the James Webb Space Telescope has revolutionized our understanding of the universe in ways that were once unimaginable. This powerful observatory, positioned nearly 1 million miles away from Earth, is equipped with advanced infrared technology that allows it to peer through cosmic dust and gas. It can observe some of the earliest galaxies formed after the Big Bang, providing insights into the universe's infancy that previous telescopes could not achieve. One of the most groundbreaking discoveries made by the James Webb Space Telescope is its ability to identify exoplanets and analyze their atmospheres. By observing the light that passes through a planet's atmosphere during transit, scientists can detect the chemical composition of those distant worlds. This capability offers the potential to find signs of habitability or even life beyond our solar system. The discoveries made have expanded our understanding of how planetary systems form and evolve. Additionally, Webb has shed light on the formation of stars and galaxies, revealing details about the processes that govern cosmic evolution. By capturing images of stellar nurseries, Webb has provided unprecedented views of the early stages of star formation. Its observations help astronomers understand how stars are born from dense clouds of gas and dust, contributing to our knowledge of the life cycle of galaxies and their ongoing changes over time. The data being collected by the James Webb Space Telescope continues to challenge our theoretical models, pushing the boundaries of what we thought we knew. The telescope's ability to look farther back in time allows researchers to study epochs of the universe that were previously obscured. As its findings unfold, we are gaining a clearer, more detailed picture of the cosmos, enriching our quest for knowledge and the mysteries it holds. Recent advancements in astrophysics have shed light on the formation of supermassive black holes, which are colossal entities residing at the centers of galaxies. Historically, researchers debated whether these giants formed from the remnants of massive stars or through the gradual accumulation of gas and other matter. Presently, a prominent theory suggests that they might originate from seed black holes created by the collapse of massive stars in the early universe, potentially merging and accumulating mass over billions of years. Another compelling concept proposes that supermassive black holes could form through a process known as direct collapse. This scenario suggests that in certain dense regions of molecular gas, gravitational forces could be strong enough to bypass the intermediate stages of star formation, allowing matter to collapse directly into a black hole. These direct collapse black holes could form sizable masses quite rapidly, setting the stage for the supermassive black holes we observe today. There's also significant interest in the idea of these black holes forming within the frameworks of dense stellar clusters. As stars orbit each other within these clusters, they can undergo gravitational interactions that lead to the formation of a more massive object. Over time, this object can grow by attracting surrounding gas and stars, ultimately evolving into a supermassive black hole at the heart of a galaxy. The cosmic timeline offers fascinating insights, as the earliest supermassive black holes appear to have emerged only a few 100 million years after the Big Bang. Their rapid formation raises questions about the nature of their birth and the environment of the early universe. As observational tools advance, astronomers continue to piece together the mysteries of supermassive black holes, probing deeper into their origins and how they influence galaxy formation and evolution across the cosmos. Gamma-ray bursts, the most energetic explosions in the universe, present significant challenges to our understanding of stellar evolution. These extraordinary events are believed to occur during the collapse of massive stars, leading to the formation of black holes or neutron stars. Yet, the precise mechanisms behind these bursts remain elusive and often defy the predictions made by conventional models of stellar life cycles and transformations. Existing theories suggest that massive stars go through predictable stages, ending in a supernova that marks the end of their lives. However, gamma-ray bursts can emit enormous amounts of energy, far exceeding what is anticipated from traditional supernova explosions. This discrepancy raises questions about what might be happening inside these dying stars. Observations of short and long gamma-ray bursts have revealed that they may result from distinct processes, yet our current models do not fully account for all the variables involved, such as the host environment or the roles of rotation and magnetic fields. Moreover, the phenomenon of gamma-ray bursts often occurs in unexpected locations and under conditions that seem contrary to established ideas. Some bursts seem to arise from the merger of compact objects like neutron stars, rather than from the explosion of an individual massive star. This revelation prompts a reconsideration of the diverse pathways that stellar remnants can take and how they ultimately lead to these powerful bursts. Research continues to evolve, with each new observation about gamma-ray bursts acting as a catalyst for revisiting and possibly redefining the relationship between stellar evolution and explosive end stages. This ongoing inquiry pushes the boundaries of our understanding and emphasizes the complexity of cosmic events, reminding us that the universe holds many secrets yet to be unraveled. Research into the atmospheres of distant planets has revealed a wealth of knowledge that stretches our understanding of planetary formation and the potential for life beyond Earth. Using advanced telescopes equipped with spectrographs, astronomers can analyze the light emitted or absorbed by these distant worlds, allowing them to determine the composition of their atmospheres. This includes elements such as hydrogen, helium, carbon dioxide, and even the presence of water vapor, which plays a crucial role in assessing habitability. One of the most exciting findings is the detection of chemical signatures that may indicate biological processes. For instance, scientists have observed the presence of methane and oxygen coexisting in the atmospheres of some exoplanets. On Earth, these gases often coexist as a result of life forms, sparking curiosity about whether similar processes are occurring elsewhere in the universe. Such discoveries challenge our understanding of how common life may be and provide enticing clues for future investigations. Moreover, studies of atmospheric dynamics on these distant planets have revealed surprising weather patterns and phenomena that differ greatly from our own experiences. For instance, some gas giants exhibit extreme winds that can reach astonishing speeds, while others have intricate cloud systems that create dazzling weather systems. These insights not only inform us about individual planets, but also about the broader mechanisms at play in atmospheric science across different celestial bodies. As technology continues to advance, future missions promise to offer even deeper insights. The James Webb Space Telescope, which has recently begun operations, is expected to dramatically enhance our ability to analyze the atmospheres of exoplanets. With its powerful instruments, scientists anticipate uncovering new details about climate trends, seasonal changes, and even the potential for ecosystems outside our solar system. Each piece of information gathered adds another layer to our understanding of the universe, fueling our curiosity and desire to explore the cosmic neighborhood. Advancements in technology and observational methods significantly enhance our understanding of the universe by allowing us to gather data that was previously unimaginable. With the development of powerful telescopes like the Hubble Space Telescope, scientists can observe distant galaxies, nebulae, and other celestial phenomena with unparalleled clarity. These observations unveil details about the formation and evolution of structures in the universe, giving us insights into cosmic history that stretch back billions of years. Moreover, advancements in detection technologies such as radio waves and gravitational waves have opened new avenues for exploration. For instance, the detection of gravitational waves has confirmed predictions made by Albert Einstein over a century ago, providing a new way to understand violent cosmic events like black hole collisions. This capability allows astronomers to study the universe in a more comprehensive manner, probing regions that are invisible to traditional optical telescopes. The development of computer algorithms and artificial intelligence has further refined our observational techniques. These tools help researchers analyze vast amounts of data collected from various instruments, identifying patterns and anomalies that might otherwise go unnoticed. As a result, we are now able to make sense of millions of celestial objects and phenomena, pushing the boundaries of our knowledge further than ever. The synergy between technology and observational methods not only enriches our comprehension of the universe, but also inspires new questions. Each discovery prompts further inquiries into the fundamental nature of reality, leading to a deeper appreciation of the cosmos and our place within it. As technology continues to evolve, so does our capacity to unlock the mysteries of the universe, revealing the intricacies of existence itself. The study of quantum fluctuations in the early universe has revealed remarkable insights into the very fabric of reality. At the moment of the Big Bang, the universe was incredibly small and extraordinarily hot, governed by the strange rules of quantum mechanics. These fluctuations, brief and fleeting variations in energy levels, likely played a crucial role in the distribution of matter and structures we observe today. One of the most significant discoveries is how these quantum fluctuations seeded the initial density variations in the universe. As the universe expanded, these uneven patches began to collapse under gravitational forces, ultimately forming galaxies, clusters of galaxies, and the vast cosmic web that holds the observable universe together. This means that the very seeds of galaxies, stars, and planets may originate from the quantum noise of the early universe. Moreover, studying these fluctuations has improved our understanding of cosmic microwave background radiation, the afterglow of the Big Bang. Patterns in this ancient radiation provide a snapshot of the universe when it was merely 380,000 years old. These patterns and their anisotropies or irregularities correspond closely with the predictions of inflationary theory, which posits a rapid expansion that followed the Big Bang. This connection bridges quantum mechanics with cosmological models and enhances our grasp of how the universe evolved. Investigations into these quantum fluctuations have also opened discussions about the nature of dark energy and dark matter. The interplay between these unknown components and the fluctuations may hold keys to some of the universe's most profound mysteries. As researchers continue to delve into this field, they uncover not just the origins of cosmic structures, but also potentially unveil deeper truths about the nature of reality itself. Recent advancements in astronomical simulations have profoundly transformed our understanding of the universe. Through sophisticated models, scientists can recreate cosmic events and processes that are far too immense and remote to observe directly. For instance, simulations of galaxy formation and evolution allow researchers to visualize how galaxies collide and merge over billions of years, revealing intricate structures and dynamics that shape the cosmos. One particularly striking impact of these simulations is their ability to illustrate the role of dark matter and dark energy in the evolution of the universe. They show how dark matter, which does not emit light, influences visible matter, ultimately leading to the formation of galaxies and clusters. As researchers run these simulations, they can fine-tune parameters and adjust initial conditions, leading to insights about the universe's structure that were previously difficult to confirm through observation alone. Simulations have also expanded our grasp of supernova explosions, black hole formation, and the behavior of neutron stars. These cosmic phenomena are central to our understanding of stellar life cycles and nuclear synthesis, the process that creates elements in stars. By modeling these explosive events, scientists have gained insights into the origins of the elements that make up our very own planet, and indeed our bodies. With these technological advancements, researchers can now better predict how the universe will evolve over time, considering factors that were once merely theoretical. This growing toolkit of simulations not only improves our understanding of cosmic processes, but also inspires a deeper curiosity about our place in the cosmos. The interplay between observation and simulation enables scientists to test their theories against the backdrop of the universe, continually refining our knowledge of the grand expanse that surrounds us. Cosmic inflation refers to a brief, rapid expansion of the universe that occurred just after the Big Bang, approximately 10 to the minus 36 seconds after the event. This theory was introduced to explain several puzzling observations about the universe, such as its uniformity and flatness. Before inflation, quantum fluctuations in energy levels caused micro-regions of space to expand exponentially, stretching the fabric of reality itself. This phenomenon caused regions of space that were once causally connected to move far apart, creating the homogeneous and isotropic universe we observe today. Inflation also provides a framework for understanding the distribution of cosmic structures, such as galaxies and clusters. During this inflationary period, tiny quantum fluctuations were magnified, seeding the variations in density that ultimately led to the formation of galaxies and large-scale structures. The slight differences in density provided the necessary conditions for gravity to pull matter together, forming the vast cosmic structures we see in the night sky today. Implications of cosmic inflation extend beyond explaining the observable patterns in the universe. It suggests that our universe could be just one of many in a multiverse, with other regions experiencing different laws of physics. This challenges our traditional understanding of reality, leading to questions about the nature of existence itself. If inflation is correct, the universe we inhabit might be a mere bubble in a much larger cosmic foam. Continued research into cosmic inflation not only delves deeper into understanding the origins of our universe, but also enhances our grasp of fundamental physics. Observations from cosmic microwave background radiation provide vital evidence supporting the inflationary model, and experiments continue to seek further signs of these early fluctuations, allowing scientists to piece together the mysteries of the cosmos. Scientists have long grappled with the peculiar movements of certain celestial bodies that do not seem to follow traditional gravitational predictions. These anomalies often manifest as unusual orbit patterns, unexpected velocities, or even a puzzling lack of visible mass to account for the gravitational forces at play. Such mysteries have prompted physicists and astronomers to explore a range of explanations beyond classic Newtonian physics. One prominent theory to explain these anomalous motions is the presence of dark matter. While it remains invisible and undetectable by traditional means, dark matter is theorized to make up a significant portion of the universe's total mass. This elusive form of matter interacts through gravity, affecting the motion of visible celestial bodies. Preliminary evidence for dark matter stems from the observation of galaxy rotation curves, which indicate that galaxies spin at speeds that should theoretically fling them apart. Yet they remain intact, suggesting that additional unseen mass must contribute to their gravitational stability. Another avenue of exploration involves modifications to existing gravitational theories. Some researchers propose adjustments to Einstein's general theory of relativity, suggesting that gravity may act differently on cosmic scales than previously understood. Theories like modified Newtonian dynamics or MOND postulate that at very low accelerations, the laws of motion differ from classical expectations, potentially providing a framework for understanding these anomalies. The search for explanations continues to evolve, driven by advances in observational technology and theoretical physics. As scientists gather more data from telescopes and other observational tools, they hope to unravel the complexities surrounding these celestial phenomena, shedding light on the fundamental laws that govern our universe. This ongoing investigation not only deepens our understanding of gravity, but also reveals the intricate tapestry of forces that shape the cosmos. Supernova explosions are monumental events in the universe, serving as the death throes of massive stars. However, despite extensive research, many aspects regarding the conditions that lead to these spectacular explosions remain shrouded in mystery. One of the key unknowns is the precise mechanism that triggers these cataclysmic ends for different types of stars, particularly for Type II supernovae, which occur from the collapse of a massive star's core. While the process of core collapse is understood in a general sense, the exact conditions leading to the explosion, like the role of rotation and magnetic fields, are still being unraveled by scientists. Another area that lacks clarity is the events leading up to the supernova explosion itself. We know that massive stars undergo fusion processes, creating heavier elements until their cores are filled with iron, which does not produce energy through fusion. But the sequence of events that turns this inert, heavy core into a supernova remains uncertain. How exactly does the core collapse lead to the rapid explosion outward? This is where theories diverge, and current models rely heavily on computer simulations that have not yet yielded a definitive answer. The observational evidence presents further complexities. For example, not all massive stars that seem ready to explode as supernova do so. Some go through a process of losing mass or burning off their outer layers before they can ignite a supernova explosion. The conditions that result in a star undergoing this mass loss are poorly understood, raising questions about how common such scenarios are and what factors ultimately dictate a star's fate. Current astrophysical research aims to deepen our understanding of these enigmatic processes. Astronomers are employing advanced telescopes and simulations to track the precursor activity of these stars more closely, as well as to study remnants of past supernovae. By piecing together this puzzle, we might one day have a clearer picture of the conditions that govern supernova explosions, ultimately revealing more about how these forces shape the cosmos. Some stars, particularly those classified as variable stars, exhibit erratic stellar flares due to magnetic activity within their atmospheres. These flares can erupt suddenly, releasing vast amounts of energy, often in the form of light and radiation. The phenomenon is especially prominent in young stars or those with strong magnetic fields, indicating a tumultuous and dynamic nature in their surroundings. The underlying mechanisms of these flares are rooted in the behavior of magnetic fields that become twisted and tangled. As the magnetic energy builds up, it can eventually release in a burst, causing a flare. This process is similar to a rubber band being stretched to its limit before snapping. For stars like the Sun, these flares can be tied to sunspots and other surface activity, illuminating the complex interplay of gravity, radiation, and magnetic forces at work. Observing these stellar flares provides valuable insights into the life cycles of these stars. For instance, frequent flaring is often seen in younger, hotter stars, suggesting they are still in a stage of rapid evolution. These energetic bursts indicate that the stars are actively nurturing their atmospheres, which can lead to planetary formation and influences on nearby environments. Thus, these erratic behaviors are not just spectacular displays of energy, but also pivotal moments that speak volumes about a star's developmental stages. By studying stellar flares, astronomers can glean critical information about the conditions surrounding stars, the activity of their magnetic fields, and the processes that govern their life cycles as they transition from youthful exuberance to stable maturity. The phenomenon known as dark flow presents a significant challenge to existing cosmological models, particularly those based on the understanding of the cosmic microwave background. Dark flow refers to the peculiar motion of galaxy clusters that seem to be moving in a unified direction, which is inconsistent with the expectations of the universe's expansion driven by dark energy. Current models suggest that, on cosmic scales, the universe should be relatively homogeneous and isotropic, meaning that matter should be evenly distributed with galaxies moving randomly relative to one another. What makes dark flow particularly perplexing is that this motion appears to be directed towards certain regions in the universe, specifically towards a constellation known as Leo. This behavior contradicts the predictions of the standard cosmological model, which posits that cosmic microwave background radiation should create a nearly uniform expansion across the universe. The observable universe is supposed to be expanding uniformly, so coherent movement of such a scale indicates that there might be undiscovered structures or forces influencing galactic motion beyond our current understanding. One compelling explanation for dark flow is the gravitational influence of structures beyond the observable universe. These could be large celestial bodies or groups of galaxies that exert a pull on nearby clusters, causing them to deviate from the expected random motion. This raises important questions about the limits of our observational capabilities and whether our models are sufficient to account for all mass and energy present in the universe. As astronomers continue to observe and study dark flow, the implications for our understanding of cosmology are profound. If this phenomenon is confirmed and understood, it could lead to new physics or adjustments to our current theories about the universe's evolution, composition, and the ultimate fate of cosmic structures. These developments will shape not only our understanding of dark flow, but could also revolutionize our entire framework of cosmological theory. Antimatter presents a captivating puzzle in our understanding of the universe's formation. While we have developed a robust theoretical framework around particle physics, the relationship between matter and antimatter remains an enigma. During the Big Bang, it is widely believed that equal amounts of matter and antimatter were created. However, the universe today is predominantly composed of matter, leaving scientists puzzled about where all the antimatter has gone. Many hypotheses have emerged to explain this discrepancy. One prominent idea is the concept of baryogenesis, which suggests that certain physical processes may have favored the production of matter over antimatter in the early universe. Under specific conditions, reactions may have produced more baryons, the particles that constitute matter, while resulting in a slight asymmetry between the two. Yet, how exactly this occurred, and whether our current understanding of the fundamental forces accounts for it, remains unclear. Moreover, antimatter's behavior is a subject of ongoing research. It interacts with matter in ways that produce gamma rays, which can be detected. Notably, when matter and antimatter meet, they annihilate each other, releasing energy in the form of light and high-energy particles. This annihilation reaction hints at the potential for antimatter to exist in isolated regions, but no substantial antimatter regions have been observed in the universe. The lack of observable antimatter could also point toward the possibility of hidden or exotic physics that we have yet to discover. Experiments at particle accelerators and observational efforts continue to seek signs of antimatter. Each new finding informs our understanding of the early universe and may one day illuminate the reasons behind this fundamental imbalance between matter and antimatter. Scientists approach the study of magnetic monopoles by exploring both theoretical frameworks and experimental pursuits. The concept of a magnetic monopole stems from the idea that isolated north or south magnetic poles could exist, unlike the dipoles we commonly observe in magnets. In theoretical physics, certain grand unified theories, which aim to unify the fundamental forces of nature, suggest that magnetic monopoles should exist. These theories propose that during the early moments of the universe, conditions were ripe for monopole formation. To find evidence for magnetic monopoles, researchers have designed various experiments, particularly using particle accelerators and astrophysical observations. Some high-energy particle collisions may have the potential to produce monopoles as a byproduct. There have been experiments that searched for monopoles in cosmic rays, which are high-energy particles originating from space. While some results have hinted at possible signatures resembling monopoles, none have been definitively confirmed. Despite this lack of direct evidence, indirect approaches lend some intriguing support to their existence. For example, certain materials display topological properties that mimic the behavior of magnetic monopoles. These properties can appear in condensed matter systems, where the effective theory suggests they behave similarly to monopoles in the underlying magnetic field, allowing scientists to explore their properties in a controlled environment. Researchers remain optimistic, continuing to develop more sensitive detection technologies and advancing theoretical models. The pursuit of magnetic monopoles is not just about confirming a speculative idea. It could also shed light on the fundamental structure of our universe, revealing new insights into the fabric of spacetime and the unification of forces. As technology advances, the prospect of discovering these elusive particles remains an exciting frontier in modern physics. Quasars, or quasi-stellar objects, remain some of the most enigmatic entities in the universe, often leaving scientists pondering their true nature. They are the brightest objects in the cosmos, outshining entire galaxies by emitting immense amounts of energy. Despite extensive research, several characteristics of quasars have yet to be fully understood, particularly concerning their origins and the mechanisms driving their extraordinary luminosity. One major area of mystery revolves around the processes that lead to their extreme brightness. Quasars are powered by supermassive black holes at the centers of distant galaxies, but the precise dynamics of how matter is accreted into these black holes and how that energy is radiated is still imperfectly understood. The energy produced during accretion creates intense radiation, but the way this energy is emitted across different wavelengths, creating the observable spectrum from radio to gamma rays, poses questions that remain unanswered. Another fascinating characteristic is their variability. Despite appearing stable over long periods, quasars show remarkable fluctuations in brightness over shorter timescales, sometimes in a matter of days or weeks. This implies that the regions of emission are comparatively small, yet the reasons behind these changes are not completely clear. Understanding this variability could provide insights into the physics of black holes and the interactions within their accretion disks. Furthermore, some quasars are observed to eject powerful jets of particles traveling close to the speed of light, extending vast distances into space. The mechanisms that produce these jets, as well as their influence on surrounding intergalactic environments, require further investigation. These unanswered questions make quasars not only remarkable objects of study, but also central to our understanding of the universe's history and evolution. Cosmic rays are highly energetic particles that travel through space at nearly the speed of light. When these particles, primarily protons but also heavier atomic nuclei and electrons, enter the Earth's atmosphere, they interact with molecules of air, creating a cascade of secondary particles. This phenomenon challenges our understanding of high-energy processes in space, because the origins of cosmic rays remain uncertain. Despite much research, the precise sources and acceleration mechanisms that propel these particles to such extreme energies continue to elude scientists. Cosmic rays provide vital clues to the workings of the universe. They are thought to originate from a variety of sources such as supernovae, pulsars, and active galactic nuclei. These locations are known for their extreme environments, where magnetic fields and shock waves can accelerate particles to extraordinary speeds. However, the sheer energy of some cosmic rays surpasses what could be expected from these sources alone, leading researchers to hypothesize about more powerful, possibly exotic processes at play, such as acceleration in the vicinity of black holes or neutron stars. The study of cosmic rays also raises questions about fundamental physics. For example, the energies of high-energy cosmic rays challenge existing theories related to particle acceleration and interactions. Observations reveal cosmic rays with energies over 1 billion times those produced by the most powerful human-made particle accelerators. This discrepancy spurs debates about conditions in the distant universe that can create such extreme energies and forces researchers to revisit our basic understanding of particle physics and cosmic events. As technology advances, scientists are utilizing sophisticated instruments and observatories to track cosmic rays better and analyze their properties. Such efforts are crucial in piecing together the intricate puzzle of the high-energy processes occurring throughout the universe. The ongoing quest to decode the mysteries of cosmic rays not only advances our knowledge about these enigmatic particles, but also enhances our understanding of the cosmos itself. The Sun's magnetic cycle, spanning roughly 11 years, influences much more than just solar weather. This cycle affects the production of sunspots, solar flares, and coronal mass ejections, all of which have significant implications for both solar and cosmic phenomena. When the Sun reaches the peak of its magnetic cycle, known as solar maximum, the activity intensifies. This surge in activity can disrupt satellites in orbit, interfere with communication systems on Earth, and even pose risks to astronauts in space. Furthermore, the Sun's magnetic activity has broader implications for our entire solar system. During periods of heightened solar activity, the solar wind, streams of charged particles emitted by the Sun, can create more intense auroras and can lead to disturbances in Earth's magnetosphere. These phenomena can affect everything from power grids to navigation systems, demonstrating how closely interconnected solar dynamics are with life on our planet. Beyond its immediate influence, the Sun's magnetic cycle plays a key role in understanding cosmic events. For example, scientists study the Sun's cycles to gain insights into how solar activity influences galactic cosmic rays that permeate our solar system. During solar maximum, the increased solar wind can shield the Earth from these cosmic rays to some degree, highlighting a complex interaction between our star and the broader cosmos. Research into the magnetic cycle of the Sun continues to reveal mysteries about solar behavior and its effects on the universe around us. By monitoring these cycles, astronomers gain valuable knowledge not only about our own star, but also about similar stars in distant solar systems, thereby enriching our understanding of astrophysical processes on a cosmic scale. As we delve deeper into solar phenomena, we unlock crucial insights into the working of the universe, reflecting the dynamic and often unpredictable nature of our star. The concept of spacetime curvature emerges from Albert Einstein's theory of general relativity, fundamentally changing our understanding of gravity and how celestial bodies interact. Instead of viewing gravity as a force acting at a distance, general relativity presents it as the warping of the fabric of spacetime around massive objects. This curvature shapes the paths that objects follow, influencing their motion through the universe. When a massive body, such as a star or planet, is placed in spacetime, it creates a depression or curve in this four-dimensional continuum. Other bodies, like moons, planets, and even light, follow these curved paths as they move through spacetime. This curving effect can be visualized as a marble rolling along a curved surface. The marble will naturally follow the curve, and its path becomes predictable based on the degree of the curve around it. This understanding provides a scientific explanation for why planets orbit stars or how galaxies interact with each other. For instance, the Earth follows an elliptical orbit around the Sun due in part to the curvature created by the Sun's massive presence in spacetime. The interplay of mass and this curvature enables celestial bodies to maintain their orbits and explains phenomena such as gravitational lensing, where light bends around massive objects like galaxies, revealing the majesty of the universe. Spacetime curvature not only aids in predicting the movement of celestial bodies, but also deepens our understanding of the interplay between mass, energy, and the very structure of the universe itself. As we continue to explore these concepts, we unveil more about the intricate dance of the cosmos. Albert Einstein's theories, particularly his general theory of relativity, revolutionized our understanding of gravity, and fundamentally changed how we view the universe. General relativity, proposed over a century ago, describes gravity not as a force in the traditional sense, but as a curvature of spacetime caused by mass. This elegant concept laid the groundwork for predicting the existence of gravitational waves, which are ripples in spacetime created by some of the most violent and energetic processes in the universe. When massive objects such as neutron stars or black holes collide or orbit each other, they disturb the fabric of spacetime, generating waves that propagate outward at the speed of light. The existence of gravitational waves was first predicted in 1915, but remained unproven for nearly a century. The implications of these waves extend far beyond mere theoretical physics. Their detection provides a new way to observe the cosmos, allowing scientists to gather information about events that were previously invisible to our traditional optical telescopes. The first direct observation of gravitational waves was made in 2015 by the LIGO Observatory. This groundbreaking event confirmed Einstein's predictions and opened a new era in astrophysics. By analyzing gravitational waves, researchers can study black hole mergers, neutron star collisions, and other extraordinary cosmic phenomena. This allows for a deeper understanding of the universe's life cycle and the forces that govern its evolution. Further investigation into gravitational waves promises to reveal even more mysteries of the cosmos. For instance, these observations could help scientists probe the early moments of the universe or enhance our understanding of fundamental physics beyond general relativity. Each detection not only confirms Einstein's theories, but also invites us to rethink our place within the cosmos, encouraging curiosity about the complex and dynamic universe that surrounds us. Black holes continue to be some of the most enigmatic objects in the universe, with many mysteries still shrouding their nature. One of the foremost questions revolves around the singularity at the core of a black hole, where gravity is believed to become infinite. Current theories suggest that our understanding of physics breaks down in this region, rendering the singularity an area where the laws of physics as we know them do not apply. This creates a paradox, as our established theories such as general relativity and quantum mechanics provide conflicting descriptions of reality. Another unknown aspect relates to the information paradox. According to quantum mechanics, information cannot be destroyed, yet when matter falls into a black hole, it appears to vanish completely. This leads to a fundamental question. Where does all the information about the matter go once it crosses the event horizon, the point of no return around a black hole? This ongoing debate has spurred various theories, including the idea that information might be encoded on the event horizon itself, but consensus remains elusive. Furthermore, our understanding is limited when it comes to the different types of black holes. While we are familiar with stellar black holes, which form when massive stars collapse, and supermassive black holes found at the centers of galaxies, the exact processes that create these various classes of black holes are not fully understood. We still have much to learn about the role black holes play in the evolution of galaxies, their formation pathways, and their relationship with dark matter. Lastly, the dynamics of black hole mergers and the ripples they create in spacetime, known as gravitational waves, are a relatively new field of study. While significant progress has been made, including the first direct detection of gravitational waves in 2015, many questions remain. How often do such mergers occur? What does their frequency tell us about the structure of the universe? The answers to these questions are critical not only to understanding black holes, but also to advancing our comprehensive knowledge of cosmology itself. Scientists study the warping of spacetime in extreme environments by utilizing a combination of observational tools and theoretical models. One of the key methods involves analyzing the gravitational effects produced by massive celestial bodies, such as black holes and neutron stars. These entities create intense gravitational fields that can warp the fabric of spacetime itself, demonstrating Einstein's theory of general relativity in action. By observing the behavior of light and other forms of radiation as they pass near these massive objects, scientists can gather valuable data on how gravity influences the curvature of space surrounding them. For instance, when light from distant stars travels close to a black hole, it can be bent or distorted due to the warped spacetime in the vicinity. This phenomenon is often referred to as gravitational lensing. By studying the patterns of light bending, researchers can infer both the mass of the black hole and the extent to which it warps spacetime. Advanced telescopes and instruments, including space-based observatories, allow scientists to detect these tiny changes in light behavior that result from gravitational interactions. Another vital approach is through the study of gravitational waves. Cosmic events such as the merger of two black holes create ripples in spacetime that travel across the universe. By using observatories like LIGO, which stands for Laser Interferometer Gravitational Wave Observatory, scientists can detect these gravitational waves. Analyzing the properties of these waves provides insights into the extreme conditions surrounding stellar collisions and how they alter the structure of spacetime during such events. Simulations also play a pivotal role in understanding spacetime warping. Using powerful supercomputers, researchers can create simulations that model the interactions of massive astrophysical objects and the resulting spacetime distortions. These simulations can visualize phenomena that are difficult to observe directly, offering further opportunities for scientists to explore the complexities of our universe. Through these diverse approaches, scientists continue to unravel the mysteries of spacetime and its remarkable behaviors in the most extreme settings. Recent advancements in understanding wormholes have propelled our knowledge from theoretical frameworks to more tangible concepts. One significant development involves advancements in quantum gravity research, which seeks to unify general relativity with quantum mechanics. These efforts have led to new insights suggesting that wormholes could actually exist, at least on a theoretical level. Researchers have been exploring specific types of wormholes, known as traversable wormholes, which would allow for travel between distant points in spacetime while maintaining stability. Another interesting aspect is the relationship between wormholes and the theory of quantum entanglement. Entangled particles exhibit a phenomenon where the state of one particle is instantly connected to the state of another, regardless of distance. Some physicists theorize that wormholes might act as a physical representation of quantum entanglement, suggesting that these hypothetical structures could provide shortcuts across the universe. This idea has led to a renewed interest in exploring their potential applications for space travel and even time travel. Despite these intriguing advances, the plausibility of traversable wormholes remains a matter of debate among scientists. The primary challenge lies in the exotic matter required to stabilize a wormhole and keep it open. This exotic matter would have negative energy density, a property not known to exist in nature. While theoretical models propose possible ways to create or harness this exotic matter, practical applications or discoveries of such materials are currently absent. The discussion around wormholes not only fuels scientific curiosity, but also evokes questions about the fundamental nature of reality. As our understanding of the universe evolves, the idea of traversable wormholes, once confined to science fiction, is slowly becoming a subject of serious scientific inquiry. The journey into the depths of space-time continues, uncovering possibilities that challenge our perception of space, time, and the very fabric of the cosmos. Time dilation profoundly influences our understanding of time and events that unfold in the universe. This phenomenon primarily arises from two key theories in physics. The first is special relativity, proposed by Albert Einstein, which suggests that time passes at different rates depending on the relative velocity of observers. As an object approaches the speed of light, it experiences time more slowly compared to a stationary observer. Essentially, this means that astronauts traveling at high speeds in space would age more slowly than people remaining on Earth. The second aspect of time dilation occurs in the realm of general relativity, where gravity plays a crucial role. According to this theory, time flows more slowly in stronger gravitational fields. For example, clocks situated near a massive object, such as a planet or a black hole, tick at a slower rate than clocks further away from such gravitational influences. This has been empirically confirmed by precise experiments, like those involving atomic clocks placed at different altitudes. These concepts have far-reaching implications for our perception of cosmic events. If a signal or light from a distant star takes millions of years to reach us, the events we observe occurred long before our reception of that light. Due to time dilation, an event that happened at a specific time for that star may not align with our timeline. This means that while we observe a supernova explosion occurring up to 10 million light-years away, it could have happened a long time ago, significantly affecting how we understand the evolution of celestial bodies. Additionally, the effects of time dilation raise fascinating questions about the perception of travel to distant galaxies. For example, if a spacecraft were to travel near the speed of light, the crew on board would perceive a fraction of the time passing compared to what is experienced on Earth. This leads to intriguing scenarios, such as the potential for astronauts traveling into the future as they return to a changed Earth, highlighting the complex interplay between time, motion, and gravity in shaping our understanding of the universe. Relativity fundamentally reshapes our understanding of simultaneity, particularly when we scale our observations to the cosmos. Traditionally, one might assume that if two events occur at the same time, they are indeed simultaneous for everyone, regardless of their location. However, Einstein's theory of relativity introduces the concept that simultaneity is not a universal truth, but rather depends on the observer's frame of reference. As objects move at high speeds, especially when approaching the speed of light, time behaves differently for different observers. For instance, two events may appear simultaneous to one observer, while another observer, moving relative to the first, may see them as occurring at different times. This effect becomes increasingly pronounced in the universe, where vast distances and high velocities are commonplace. For example, when light from a distant supernova reaches Earth, it carries information that has traversed space for millions of years, meaning that our observation is always a snapshot of the past, influenced by the position and motion of the observer. Additionally, this leads to phenomena that can seem counterintuitive. Take, for instance, two observers in different parts of the universe, each experiencing their respective realities. When they attempt to synchronize their clocks, they may find that what they consider simultaneous may not align due to their distinct relative velocities and gravitational influences. This divergence constructs a complex tapestry of reality, where what one person perceives is not the same for another, resulting in potential misunderstandings about shared experiences in space and time. This revolutionary idea challenges us to consider the universe in a fluid, dynamic manner. As we delve deeper into cosmic scales, such as galaxies colliding or binary star systems in motion, our understanding of time and space continues to evolve. The effects of relativity remind us that the cosmos operates on principles that may differ drastically from our everyday experiences, urging us to re-evaluate the very nature of reality. Quantum mechanics plays a crucial role in our understanding of spacetime, particularly when we delve into the fabric of the universe at its most fundamental level. At the heart of this relationship is the realization that the very structure of space and time may not be as continuous as once thought. Instead, emerging theories suggest that spacetime could have a discrete nature at the smallest scales, fundamentally altering how we perceive the universe. One of the significant implications of quantum mechanics for spacetime is the concept of quantum entanglement. This phenomenon illustrates how particles can become linked in such a way that the state of one particle instantly affects the state of another, regardless of the distance separating them. Such entanglement challenges traditional notions of locality and hints at a deeper interplay within the structure of spacetime itself. As various particles influence each other across vast distances, it leads scientists to consider whether spacetime is a smooth continuum or a series of interconnected points. Another area where quantum mechanics influences our understanding of spacetime is through the study of black holes. When matter collapses under its gravitational pull, creating extreme warps in spacetime, quantum mechanics suggests that information is never truly lost, even within these enigmatic regions. This intersection of quantum physics and general relativity raises profound questions about the nature of reality, existence, and the ultimate fate of information in our universe. Furthermore, the quest to develop a unified theory that combines quantum mechanics and general relativity, often referred to as quantum gravity, continues to inspire new insights. Researchers are exploring ideas such as string theory and loop quantum gravity, which propose that the fundamental building blocks of spacetime are not particles but rather tiny vibrating strings or discrete loops. These theories aim to bridge the gaps between the quantum world and the cosmic ballet of galaxies and gravitational waves, fundamentally reshaping our understanding of the universe's architecture. The concept of space-time foam introduces a fascinating and intricate idea in the realm of theoretical physics. This concept suggests that on extremely small scales, around the size of the Planck length, space-time exhibits a turbulent, frothy structure. It is believed that this foamy nature arises due to quantum fluctuations, where tiny ripples create a dynamic, ever-changing landscape of space and time. This is particularly significant when considering the conditions of the early universe, which was vastly different from what we observe today. During the initial moments after the Big Bang, the universe underwent rapid expansion and extreme temperatures. In this turbulent environment, space-time foam may have played a critical role. It implies that the smooth fabric of space-time, which we are accustomed to perceiving, might have been highly irregular, influencing the behavior of particles and energy at the very foundational level. These fluctuations could have had profound effects on the formation of structures and the distribution of matter as the universe continued to evolve. One of the intriguing aspects of space-time foam is its potential connection to theories of quantum gravity. A comprehensive understanding of how quantum mechanics and general relativity interplay is necessary to fully grasp the early universe's dynamics. If space-time is indeed foamy, it provides a compelling framework for exploring how gravity behaves at quantum scales, which has direct implications for the evolution of the cosmos from its inception. The exploration of space-time foam and its effects leads to many questions about the nature of reality itself. As scientists continue to study these early moments, they seek not only to understand the universe's birth, but also to bridge the gap between quantum theories and classical descriptions of gravity. This search could unveil new insights that fundamentally reshape our comprehension of the universe's history and its ultimate fate. The exploration of space-time continues to capture the imagination of scientists and researchers around the world. Future experiments aimed at deepening our understanding of this fundamental concept will likely include advancements in particle physics, astrophysics, and gravitational wave detection. One such endeavor is the upcoming generation of gravitational wave observatories. These facilities will enhance our ability to detect ripples in space-time caused by colossal events, such as merging black holes and neutron stars. By observing these phenomena, scientists hope to glean insights into the fabric of the universe and potentially uncover new aspects of general relativity. Quantum physics also holds the key to unraveling the mysteries of space-time. Experiments that focus on quantum entanglement and the behavior of particles at extremely small scales could reveal how gravity operates at the quantum level, shedding light on the often perplexing relationship between gravity and quantum mechanics. Projects like the Large Hadron Collider continue to probe the fundamental particles that compose our universe. Theoretical physicists are eager to explore concepts such as string theory and loop quantum gravity, which aim to unify the principles of quantum mechanics and general relativity. Another exciting prospect is the Enhanced Laser Interferometer Gravitational Wave Observatory, which will improve sensitivity and allow for the detection of even more subtle gravitational waves. As this observatory operates, the data collected will open the door to understanding time dilation and how space is intertwined with gravity. Coupling this with simultaneous observations from advanced telescopes will enable a multifaceted approach to studying cosmic phenomena, providing a clearer picture of the universe's structure. Furthermore, proposed missions to study extreme environments, like the Event Horizon Telescope, which famously imaged a black hole, can provide empirical data that directly tests theories of spacetime. Efforts to explore dark matter and dark energy are also crucial, as these enigmatic forces play a significant role in the expansion of the universe and could lead to revolutionary insights into the nature of spacetime itself. Each of these experiments holds the promise of not just answering lingering questions, but perhaps raising new ones that will continue to guide our quest for knowledge. The classification of celestial objects such as planets, moons, and other bodies relies on several criteria based on their characteristics, composition, and orbital dynamics. A planet is defined primarily as an astronomical object that orbits a star, is spherical due to its own gravity, and has cleared its orbital path of other debris. As we continue to explore our solar system and beyond, these definitions often adapt to encompass new discoveries and a better understanding of celestial mechanics. A moon, on the other hand, is a natural satellite that orbits a planet. Moons can vary dramatically in size and composition, from the large Ganymede, which surpasses even the planet Mercury in size, to the small, irregularly shaped bodies that orbit our own planet. The existence of moons is often tied to their host planet's gravitational influence, and in many cases, they can provide critical insights into the history and formation of the planet they orbit. The term celestial body is a broader umbrella that encompasses any natural object in space, including stars, planets, moons, asteroids, comets, and meteoroids. This classification is constantly evolving, particularly as new information becomes available from telescopes and space missions. For example, the discovery of numerous celestial objects in the Kuiper Belt and beyond has led to debates about what constitutes a planet, particularly with the status of Pluto being downgraded to that of a dwarf planet in 2006. Discussions around classification can spark controversy within the scientific community, prompting a re-evaluation of established definitions as new discoveries are made. As our technology advances and we venture further into the universe, our understanding of planets, moons, and celestial bodies continues to expand, highlighting the dynamic nature of astronomical classification. Scientists employ several methods to determine the ages of stars at different stages of their life cycles, each tailored to the unique characteristics of the star. One of the primary techniques involves studying the properties of a star's light. By analyzing its spectrum, astronomers can determine its temperature, luminosity, and chemical composition. These factors help classify the star on the Hertzsprung-Russell diagram, a vital tool that correlates a star's brightness and temperature with its evolutionary stage. Another method involves understanding the star's mass. More massive stars evolve quickly, spending only a few million years in their most luminous phases. On the other hand, smaller stars can live for billions of years. This mass-luminosity relationship provides a framework to estimate age. When scientists observe a star that is in a stable phase, such as the main sequence, they can gauge its mass and correlate it with age, providing insights into its life history. For stars in specific clusters, including globular and open clusters, scientists also utilize the concept of stellar populations. All stars in a cluster are believed to have formed around the same time, so by identifying the most massive stars that have already left the main sequence, astronomers can estimate the cluster's age. This method is particularly useful since it gives a collective age for a group of stars rather than focusing on individual stars. Additionally, more advanced techniques involve examining the abundance of certain elements. Stars synthesize elements as they age, and the ratios of heavy elements to light elements can serve as a cosmic fingerprint of their age. By comparing these ratios with models of stellar nucleosynthesis, researchers can derive more precise age estimates. Through these various methods, scientists piece together a detailed picture of a star's life cycle and its journey through the cosmos. Asteroid belts are fascinating regions in our solar system, filled with a variety of rocky debris left over from the early stages of planetary formation. The most well-known of these is the asteroid belt located between Mars and Jupiter, where millions of asteroids orbit the Sun. These remnants offer valuable clues about the conditions and processes that shaped the planets we know today. By studying these celestial objects, scientists can gain insights into the primordial materials that formed our solar system around 4.6 billion years ago. The significance of asteroid belts extends beyond mere remnants. They can act as time capsules, preserving the history of our solar system's formation. Each asteroid is essentially a fragment of the past, reflecting the composition of material that was present when the planets were forming. Analyzing asteroids can reveal the methods by which they aggregated and evolved, shedding light on scenarios of both growth and destruction in planetary development. For instance, some asteroids may harbor organic compounds, offering clues about the origins of life on Earth. Asteroid belts also prompt intriguing questions about why some material coalesced into planets while others remained as smaller bodies. The gravitational influence of nearby planets, particularly massive Jupiter in the case of our asteroid belt, played a significant role in this process. Jupiter's strong gravitational pull prevented the asteroids from merging into a larger planet, leading to the formation of a vibrant collection of smaller bodies instead. This dynamic balance of forces fuels research into planetary migration and the variations in planetary systems around other stars. Finally, the mysteries held within asteroid belts may expand our understanding of the solar system's future. These regions can be a source of raw materials, offering potential resources for space exploration and colonization. As technology advances, the prospect of mining asteroids for metals, water, and other materials becomes increasingly plausible. The study of these belts not only enriches our knowledge of solar system history, but also prepares us for future ventures beyond Earth. What role do neutron stars play in the understanding of the universe, particularly in relation to gravitational waves? Neutron stars come into existence following the dramatic fate of massive stars that have exhausted their nuclear fuel. When these stars reach the end of their life cycle, they can no longer support their own weight through nuclear fusion, leading to a catastrophic implosion. This implosion results in a supernova explosion, scattering the outer layers of the star into space while compressing the core. If the core's mass is sufficient, typically between 1.4 and 3 times that of our Sun, the gravitational collapse forces protons and electrons to combine, creating neutrons. This process produces a neutron star, which becomes one of the densest objects in the universe. The unique properties of neutron stars are quite astonishing. A neutron star typically measures only about 20 kilometers in diameter, yet contains a mass greater than that of an entire sun. Their remarkable density means that a single teaspoon of neutron star material would weigh around 6 billion tons on Earth. This extraordinary compression leads to their surface gravity being tremendously powerful, over 2 billion times that of Earth's gravity. Another fascinating aspect of neutron stars is their rotation. Many neutron stars are born spinning rapidly due to the conservation of angular momentum during their collapse. These rapidly rotating neutron stars, known as pulsars, emit beams of radiation that sweep across the sky like a lighthouse beacon, leading to periodic bursts of radio waves. Their rotation can be incredibly fast, with some pulsars completing several hundred rotations each second, making them among the most efficiently rotating objects in the universe. Neutron stars also exhibit extraordinary magnetic fields, which are trillions to quadrillions of times stronger than Earth's magnetic field. This immense magnetic force can influence the surrounding space, impacting how these stars emit radiation and interact with their environment. These combined features illustrate the incredible and extreme nature of neutron stars, providing a window into the violent and transformative processes governing the life cycles of stars in our universe. Brown dwarfs possess unique characteristics that set them apart from both stars and planets. They are often described as having masses between 13 and 80 times that of Jupiter. This range places them below the threshold needed for sustaining hydrogen fusion, a process typically associated with stars. Instead, they accumulate mass and generate heat through gravitational contraction and deuterium fusion, which occurs due to the presence of the heavier form of hydrogen, deuterium, early in their existence. Their surface temperature can vary significantly, often ranging from around 1,000 to 2,500 degrees Celsius. This temperature is relatively cool when put into perspective with traditional stars, making brown dwarfs glow dimly in the infrared spectrum rather than the visible light that most stars emit. This characteristic further emphasizes their subtler nature compared to their stellar counterparts. Their low luminosity requires powerful telescopes equipped with infrared detectors to observe them effectively. The term failed stars stems from their inability to reach the necessary conditions for nuclear fusion of hydrogen into helium, the process that powers true stars. During formation, brown dwarfs may experience a brief phase of deuterium fusion, but they ultimately lack the mass to sustain long-term hydrogen fusion. Hence, they occupy a fascinating niche in the cosmic tapestry, serving as a bridge between massive planets and fully fledged stars. Intriguingly, brown dwarfs can also have atmospheres rich in complex molecules such as water and methane, which further distinguishes them in the astronomical community. Their study provides valuable insights into the processes of star formation, the formation of solar systems, and the diverse array of celestial bodies that populate our universe. Black holes and neutron stars, both thrilling endpoints of stellar evolution, have profound ways of interacting with the universe around them. Neutron stars, incredibly dense remnants of supernova explosions, can emit powerful beams of radiation due to their rapid rotation and strong magnetic fields. These celestial objects can interact with their surroundings by pulling in material from companion stars, leading to intense phenomena such as X-ray bursts. Black holes, on the other hand, exert an immense gravitational pull that can influence nearby stars and gas clouds, creating accretion disks of swirling matter. The energy released from these disks is often observed as X-ray emissions, marking the regions surrounding these enigmatic entities as some of the hottest and most energetic sites in the universe. The mysteries of both black holes and neutron stars unravel further when we examine their gravitational interactions within binary systems. Neutron stars can collide with each other, resulting in cataclysmic events that release gravitational waves. The merging of these compact objects is a spectacular event, as it not only produces powerful bursts of gamma rays, but also creates heavy elements like gold and platinum in the aftermath. Observations have provided crucial insights into these mergers, but have also raised pressing questions about the exact conditions that allow them to occur and the nature of matter at such extreme densities. Black holes, particularly supermassive ones at the centers of galaxies, continue to puzzle scientists. While we can observe their influence on surrounding stars and gas, direct observation remains elusive due to their very nature. They present a conundrum in the laws of physics, where general relativity clashes with quantum mechanics. This intersection is at the core of many unresolved questions about the fundamental workings of time, space, and information. The concept of what happens to matter and information when it crosses the event horizon of a black hole is one of the most debated topics among physicists. As we improve our observational technology, such as gravitational wave detectors and advanced telescopes, we inch closer to unlocking these mysteries. Each discovery leads to new questions, creating a tantalizing picture of the universe's complexity. Understanding the interactions of black holes and neutron stars is not just about what they can tell us about themselves, but also about the fundamental processes that govern the cosmos. Galaxies are born from the intricate interplay of matter and energy in the universe. Initially, the universe was a hot, dense sea of particles and radiation. Over billions of years, small fluctuations in density occurred in this primordial soup. Regions with slightly higher densities began to attract more matter due to gravity, pulling in gas and dark matter. As this matter coalesced, it formed the first stars, which eventually grouped together to create galaxies. The processes that led to galaxy formation are tied to the large-scale structure of the universe. The gravitational pull of dark matter did not just help form individual galaxies, it created vast cosmic filaments and clusters where galaxies would later gather. Star formation within these nascent galaxies played a critical role as well. Massive stars exploded in supernovae, enriching the surrounding gas with heavier elements, which in turn facilitated the formation of new stars and planets. This cycle contributed to a range of galaxy types, from spirals to ellipticals. Despite a solid understanding of how galaxies form, many mysteries persist. For instance, scientists are still puzzled by the precise role of dark matter in galaxy evolution. While its presence is inferred from gravitational effects, How it interacts with normal matter during the formation process remains poorly understood. Additionally, the initial conditions that led to the formation of structures in the early universe, known as the cosmic web, are still not fully explained. Another enigmatic aspect is the impact of supermassive black holes found at the centers of most galaxies. Their formation and growth appear to influence galaxy development in significant ways. The mechanisms behind their creation and the relationship between galaxies and their central black holes raise questions that challenge our current theories. These ongoing inquiries showcase the complexity of the cosmos and leave room for future discoveries that can deepen our understanding of galaxy formation. The study of cosmic dust plays a crucial role in understanding the chemical evolution of the universe. Cosmic dust, which consists of tiny particles ranging from carbon compounds to silicates, acts as a witness to the processes that shape galaxies and stars. As dust forms in the cooling regions of space, often produced by dying stars, it carries information about the elemental composition and the historical events of the cosmos. When we observe cosmic dust, we can decipher the various elements and molecules that exist in space. This is key to piecing together the timeline of the universe's chemical evolution. For instance, during the formation of stars and supernova explosions, heavy elements are synthesized and ejected into the interstellar medium, enriching the surrounding gas and dust. The composition of cosmic dust can indicate the types of stars that have lived and died in a region, providing insight into the recycling of material throughout cosmic history. Furthermore, studies of cosmic dust and its properties can guide astronomers in understanding how galaxies evolve over time. As dust interacts with light from stars and other cosmic bodies, it absorbs and re-emits energy, allowing scientists to analyze the light signatures and determine the temperature, density, and composition of the dust. The presence of specific elements in cosmic dust can reveal the conditions of the early universe, shedding light on how the first stars and galaxies formed. Ultimately, cosmic dust serves as a cosmic archaeologist, leaving clues about our universe's past in its tiny particles. Every speck tells a story, illuminating the complex web of elemental life that has existed from the very beginning, as well as the ongoing processes that continue to shape the universe we observe today. Studying star clusters is vital for understanding galactic evolution because they serve as important laboratories for astronomers. These clusters, which group stars that formed from the same molecular cloud, provide insight into the processes that govern star formation, stellar evolution, and the dynamics of galaxies. Each cluster retains a snapshot of its birth conditions, allowing scientists to trace how galaxies evolve over time. There are two main types of star clusters: open clusters and globular clusters. Open clusters tend to be younger and contain fewer stars, while globular clusters are older, more densely packed, and often home to hundreds of thousands of stars. By analyzing the properties of these clusters, such as their age and composition, researchers can glean information about the physical conditions in the early universe and how stars contributed to the chemical enrichment of their surroundings. As clusters evolve, they interact with their environment, leading to phenomena such as the formation of new stars or the merging of clusters. These interactions provide clues about the gravitational influences within a galaxy, including the behavior of dark matter, which makes up a significant portion of the universe. Observations of star clusters help to refine models of galaxy formation and transformation, permitting astronomers to piece together a comprehensive history of how galaxies like our Milky Way have changed over billions of years. In addition, star clusters can serve as tracers of the galaxy's gravitational field and dynamics. Their movements reveal information about how mass is distributed within a galaxy, including the effects of unseen matter. Overall, star clusters are not just collections of stars. They are foundational to our understanding of the life cycle of galaxies. Scientists investigate the origins of quasars primarily through a combination of observational astronomy and theoretical modeling. Quasars, or quasi-stellar objects, are incredibly luminous and distant sources of energy that emit vast amounts of light, often outshining entire galaxies. Researchers utilize powerful telescopes that can observe these objects across various wavelengths, including radio, optical, and X-ray. By capturing the light emitted or absorbed by quasars, scientists can determine their composition, velocity, and distance from Earth. Understanding what causes quasars begins with the study of their supermassive black holes. At the center of most quasars lies a black hole with a mass millions to billions of times that of the Sun. The intense gravitational pull of these black holes draws in surrounding matter, forming an accretion disk of gas and dust. As this matter spirals inward, it heats up to extreme temperatures, resulting in the release of energy in the form of radiation. By analyzing the light profiles from these accretion disks, scientists can gather evidence about the black hole's properties and activity. Additionally, scientists investigate the impact of quasars on their surroundings by observing how their energy output influences the intergalactic medium. The intense radiation emitted can drive out gas from nearby galaxies, affecting star formation rates. This interaction can lead to what is known as feedback, where the energy released by quasars shapes the evolution of galaxies and their baryonic matter. Advanced simulations recreate these scenarios, allowing researchers to visualize and predict how quasars interact with and transform surrounding cosmic structures. The study of quasars not only sheds light on their own origins, but also offers crucial insights into the formation and evolution of the universe. Through ongoing research, scientists continue to unravel the mysteries surrounding these enigmatic objects and their role in the cosmic landscape. The large-scale structures of the universe, such as galaxies, galaxy clusters, and cosmic filaments, provide crucial insights into the formation and evolution of the cosmos. These structures are not randomly dispersed, but exhibit a fascinating web-like pattern, often described as the cosmic web. This intricate arrangement raises significant challenges for our cosmological models, which attempt to explain how matter and energy interact across vast distances. Our current understanding, primarily based on the Big Bang theory and the framework of general relativity, predicts that the universe should display uniformity on large scales. However, observations reveal that while the universe appears homogeneous and isotropic when viewed over an immense expanse, there are slight fluctuations in the density of matter that lead to the formation of structures. These variations, known as the cosmic microwave background radiation, hint at the gravitational effects of dark matter, an elusive substance that remains poorly understood. Furthermore, the existence of dark energy complicates our models even further. Dark energy is believed to drive the accelerated expansion of the universe, yet its precise nature is still a mystery. As researchers study the relationship between large-scale structures and this enigmatic energy, they are forced to refine existing theories or develop new ones that can better incorporate these observations. The way galaxies are distributed and their motion through the universe can profoundly affect our interpretations and predictions regarding cosmic evolution. In this ongoing quest, scientists rely on advanced simulations and observational technologies to explore these cosmic puzzles. The challenge is not just to account for the structures we see, but also to understand their origins and roles within the broader cosmological narrative. This means that our models of the universe are dynamic, continually adapting as we uncover new secrets of the cosmos, keeping alive the excitement of discovery in the field of cosmology. The cosmic web is a vast structure that represents the largest scale of the universe, comprised of galaxies, galaxy clusters, and vast voids. Imagine the universe as a three-dimensional spiderweb, with threads connecting clumps of galaxies. This intricate network forms by the action of gravity, pulling matter together over billions of years. While we observe local clusters of galaxies, the cosmic web stretches across the universe, revealing patterns that tell us how matter has evolved since the Big Bang. Current understanding tells us that the cosmic web is primarily composed of dark matter, which, despite being invisible, influences the gravitational pull that shapes the universe's structure. Observations have indicated that galaxies are not randomly distributed. They tend to lie along the filaments of the web. These filaments of hydrogen gas and dark matter create an interconnected network, while the voids between them can be hundreds of millions of light-years across, largely empty of galaxies. Despite significant advances in our understanding, pressing questions about the cosmic web's formation remain. Scientists are still unraveling the exact processes that led to its structure, particularly concerning the role of dark energy in the universe's expansion. Additionally, the transition from homogeneous matter distribution shortly after the Big Bang to the intricate web we observe today is not yet completely understood. What triggered the initial density fluctuations that resulted in the formation of these filaments and voids continues to intrigue researchers. Furthermore, the interactions between galaxies within the cosmic web, such as mergers and gravitational influences, pose additional mysteries. The processes governing star formation and the ways galaxies interact are inextricably linked to the cosmic web's dynamics. As telescopes improve and simulations become more sophisticated, scientists hope to answer these questions, unveiling how the magnificent structure we see today came to be. Galactic mergers play a fundamental role in shaping the evolution of galaxies throughout the vast timeline of the universe. When two galaxies collide, they do not simply pass through one another. Instead, their gravitational interactions can lead to dramatic transformations. These interactions often trigger bursts of star formation as the dense gas clouds within the merging galaxies collide and compress. This phenomenon can result in the formation of new stars at an accelerated rate, adding to the overall mass and brightness of the resulting galaxy. As the merger progresses, the galaxies can undergo significant structural changes. Their shapes may be altered from relatively orderly disk forms into more chaotic elliptical configurations. This transformation can lead to increased complexity in the galaxy's dynamical properties and can also facilitate the growth of supermassive black holes at their centers. When two galaxies collide, their central black holes can ultimately merge as well, creating even more powerful black holes and influencing the galactic environment over time. Over cosmic timescales, galactic mergers contribute to the hierarchical model of galaxy formation. This model suggests that smaller galaxies combine to form larger ones, leading to the creation of massive structures we observe today. Observations indicate that the majority of galaxies have experienced at least one significant merger, and many have undergone multiple mergers throughout their history. Each merger not only reshapes individual galaxies, but also contributes to the large-scale structure of the universe. The aftermath of galactic mergers can influence the future evolution of galaxies as well. The remnants of a merger may become a more stable galaxy, one that is more resistant to future interactions. However, it may also be more prone to run-ins with other nearby galaxies. As galaxies continue to evolve, these mergers establish a dynamic cosmic environment that drives the formation of new structures and the continuous cycle of creation and destruction in the universe. While astronomers have made significant progress in understanding dark matter, many mysteries remain regarding its distribution on cosmic scales. One of the key unknowns is how dark matter is organized in the large structures of the universe, such as galaxy clusters and filaments of the cosmic web. Observations suggest that dark matter is not evenly distributed. Instead, it tends to clump together under the influence of gravity. This behavior leads scientists to question how these clumps formed and evolved over time. Another area of uncertainty involves the nature of dark matter itself. The leading theories propose that it is made up of particles that interact very weakly with ordinary matter. However, the specific particles remain unidentified, complicating our ability to map dark matter's exact distribution. Current models of cosmic structure formation rely heavily on simulations that assume a particular type of dark matter, but the parameters of these models are still being refined as new observational data is collected. Additionally, the interaction between dark matter and galactic formation presents challenges for researchers. Galaxies are thought to form within dark matter halos, yet the relationship between the properties of these halos and the observable characteristics of galaxies, such as their mass, size, and star formation rates, is an ongoing mystery. These complexities raise questions about how tightly linked dark matter is to visible matter in galaxies. Finally, the overall large-scale structure of the universe, influenced by dark matter, continues to inspire investigation. Astronomers are working to decipher the precise distribution of dark matter on cosmic scales and how it relates to phenomena such as cosmic microwave background radiation. As technology advances and observational techniques improve, scientists remain hopeful that they will uncover deeper insights into the elusive presence of dark matter in our universe. Cosmic strings are hypothetical one-dimensional defects in the fabric of spacetime, much like cracks in a sidewalk. These strings are predicted by certain theories in physics, particularly those related to the early universe during its rapid inflationary phase. They are believed to have formed as a result of symmetry-breaking processes that occurred when the universe cooled down after the Big Bang, similar to how a magnet can form domains. The presence of cosmic strings could offer profound insights into the universe's structure. They are thought to be incredibly dense and could affect the surrounding spacetime, creating gravitational fields strong enough to distort light and matter. One intriguing aspect of cosmic strings is how they might act like gravitational lenses. As light passes near a cosmic string, it is bent around the string, which could result in multiple images of distant objects, a phenomenon scientists continue to explore. While no direct evidence for cosmic strings has yet been observed, their implications stretch far beyond mere curiosities. They could offer clues about the unification of forces in physics, giving us glimpses into conditions that existed shortly after the Big Bang. If cosmic strings do exist, their study could help bridge the gap between general relativity, which describes gravitation at a large scale, and quantum mechanics, which explains the smallest particles of the universe. The search for cosmic strings involves a variety of astrophysical techniques, including analyzing cosmic microwave background radiation and gravitational wave detections. As researchers continue to investigate, they hope to hone in on whether these bizarre structures are indeed part of the universe's grand tapestry or merely theoretical constructs. Discovering the truth about cosmic strings could significantly alter our grasp of the cosmos and enhance our understanding of its complex architecture. Gravitational settling of matter plays a significant role in the intricate process of galaxy formation. As the universe expanded after the Big Bang, regions of space began to clump together due to gravitational attraction. These clumps, composed of gas, dust, and dark matter, experienced increased density over time. The gravitational pull in these areas caused matter to settle and accumulate, leading to the formation of protogalaxies, early structures that would eventually evolve into full-fledged galaxies. As the gas and dust consolidated, they became increasingly dense, triggering conditions that could support nuclear fusion. This fusion process birthed stars, and these newly formed stars further influenced their surroundings through intense radiation and stellar winds. These phenomena can drive away some of the surrounding gas while compressing other regions, encouraging even more star formation. Therefore, gravitational settling does not merely create a repository of matter, it sets in motion a complex series of interactions that can stimulate the birth of many new stars. Additionally, the settling of various types of matter affects the overall structure of galaxies. For instance, as stars form and exhaust their nuclear fuel, they may explode in supernova events, dispersing heavier elements back into their surroundings. Some of this material will be drawn back into the galaxies, enriching the interstellar medium. This process creates a continuous cycle of stellar birth, death, and rebirth, all driven by gravitational forces acting on the settled matter. The balance of this matter settling, alongside the influence of dark matter, ultimately shapes the different types of galaxies we observe today. Spirals, ellipticals, and irregulars all owe their unique features to how matter has settled and evolved under the ever-present force of gravity. Understanding this aspect of galaxy formation offers valuable insights into the history and evolution of our universe. The density of the universe plays a crucial role in determining its ultimate fate, influencing the cosmos in profound ways. To understand this relationship, we need to consider the effects of density on gravitational forces and the expansion of the universe. Essentially, the density can dictate whether the universe keeps expanding indefinitely, slows down, or ultimately contracts. Astronomers categorize the universe into three main scenarios based on its density relative to a critical value. If the density is higher than this critical threshold, the universe is considered closed. In this scenario, gravity would slow the expansion over time, potentially leading to a reversal where the universe collapses back in on itself in a process called the Big Crunch. This is a dramatic end, where galaxies ultimately collide and coalesce, returning all matter to a singular point. Conversely, if the universe's density is less than the critical value, it is termed open. This type of universe would continue to expand forever, albeit at a decelerating rate. While the expansion would never cease entirely, galaxies would move further apart endlessly, leading to a frigid state where stars burn out and galaxies drift into oblivion, known as the heat death. This scenario paints a bleak picture of an ever-expanding universe that loses its structure and energy over trillions of years. Then there is the flat universe, where the density aligns perfectly with the critical value. In this balanced state, expansion would slow asymptotically, approaching but never quite reaching a halt. This delicate equilibrium leads to a universe that expands forever, but at an increasingly slower rate. Current observations suggest that our universe aligns closely with this flat scenario, especially after considering the influence of dark energy, a mysterious force accelerating the expansion. This complex interplay of density, gravity, and expansion sets the stage for an uncertain but compelling cosmic future. Globular clusters are tightly packed groups of stars, often found orbiting the outskirts of galaxies. Their life cycle is shrouded in various mysteries, primarily because these ancient stellar formations can be billions of years old, with origins that remain somewhat elusive. Scientists believe that globular clusters formed early in the universe's history, potentially from the merging of smaller star clusters or as remnants of primordial gas clouds. However, the precise mechanisms of their formation continue to prompt intriguing questions. One of the more puzzling aspects of globular clusters is their stellar populations. Many of these clusters exhibit what is called multiple populations, meaning they contain stars of different ages and chemical compositions. This observation challenges the conventional understanding of stellar evolution and raises questions about how these disparate populations came to exist within the same cluster. For instance, how did the first generation of stars create the conditions for the subsequent generation? Understanding the interplay between stellar evolution and the complex dynamics within these clusters remains a fascinating area of research. Another mystery pertains to the fate of globular clusters as they age. While it is known that they can survive for billions of years, they are not immortal. Various forces, such as tidal interactions with the host galaxy and encounters with other star clusters, can eventually strip them of their stars or lead to their disintegration. Yet some clusters linger long after their formation, which opens up questions about the measures that contribute to their longevity. What intrinsic characteristics allow certain globular clusters to withstand these cosmic challenges better than others? Moreover, the presence of black holes within some globular clusters adds another layer of intrigue. Observations suggest that there may be intermediate mass black holes lurking at their centers, possibly formed through the merger of smaller black holes or from the collapse of massive stars. The role of these black holes in the dynamics of globular clusters could provide insight into both stellar evolution and the characteristics of black holes themselves. The study of globular clusters thus not only reveals the secrets of individual stellar populations, but also sheds light on broader cosmic phenomena. Researchers study the dynamics of galaxy clusters by employing a combination of observational techniques and theoretical models, providing insights into these vast cosmic structures. Galaxy clusters are collections of dozens to thousands of galaxies bound together by gravity, making them the largest known gravitationally bound structures in the universe. One major approach is the use of powerful telescopes, both ground-based and space-based, that capture light across various wavelengths, including optical, infrared, and X-rays. This multi-wavelength perspective allows scientists to observe different components, such as the galaxies themselves, the hot gas that permeates the clusters, and even the presence of dark matter. X-ray emissions are particularly revealing, as the hot gas surrounding galaxies reaches temperatures in the millions of degrees, glowing brightly in the X-ray spectrum. By analyzing the intensity and distribution of these emissions, researchers can assess the thermal dynamics of the gas and infer the mass of the entire cluster. This gives clues about the gravitational interactions amidst the galaxies and the overall mass distribution, including the elusive dark matter that remains invisible to regular observation, yet shapes the structure of the universe. Scientists also deploy simulations to model the gravitational interactions within galaxy clusters. By comparing simulations with observational data, researchers can refine their understanding of how these clusters form and evolve over time. The dynamics revealed through simulations can help answer fundamental questions about the behavior of matter in extreme gravity, the role of dark energy, and the fate of the universe itself. Furthermore, galaxy clusters can act as cosmic laboratories for studying the properties of the universe on a grand scale. They hold secrets about the way galaxies form and evolve, the influence of dark matter in shaping visible structures, and the dynamics of large-scale cosmic structures. Each galaxy cluster carries with it a part of the universe's history, providing clues about the past turmoil of cosmic evolution and offering a glimpse into the future of our ever-expanding universe. Studying the cosmic microwave background, often abbreviated as CMB, provides invaluable insights into the early universe. This faint glow of radiation fills the cosmos and is a remnant from the time just after the Big Bang, around 380,000 years post-event, when the universe cooled sufficiently for protons and electrons to combine and form neutral hydrogen. This shift allowed light to travel freely, leading to the emission of the CMB we detect today. One of the most compelling aspects of the cosmic microwave background is its temperature fluctuations. These variations, though incredibly subtle, reveal vital information about the density, composition, and evolution of the universe. By meticulously analyzing these minute differences in temperature, scientists construct maps that illustrate regions of higher and lower density. These maps enable researchers to trace the seeds of galaxies and large-scale structures that began forming in the universe's infancy, allowing for a deeper understanding of how the cosmos grew and evolved. Furthermore, the CMB offers insights into fundamental cosmological parameters, such as the rate of expansion of the universe, known as the Hubble constant, and the amount of dark energy and dark matter existing within it. By examining the characteristics of the CMB, physicists have refined their models of cosmic evolution and made predictions about the universe's fate. For instance, the data suggests that the universe is made up of about 70% dark energy, 25% dark matter, and only 5% ordinary matter. Moreover, the CMB acts as a laboratory for testing theories of physics. Anomalies in the CMB data may point to physics beyond current understanding, inviting new hypotheses about the fundamental forces and particles. This exploration not only deepens our knowledge of the universe, but also fuels the search for a unified theory that can explain the behavior of all forces in nature. The insights gained from the cosmic microwave background serve as a foundation for our ongoing quest to unravel the mysteries of the cosmos. Several innovative technologies are emerging as frontrunners for future space exploration. One of the most exciting advancements is propulsion systems, particularly those that utilize ion propulsion. This technology uses electric fields to accelerate ions, allowing spacecraft to achieve higher speeds and travel longer distances without carrying large quantities of fuel. Such systems could enable missions to distant planets and even interstellar travel, opening new frontiers for human exploration. Another noteworthy development is the progress in robotics and artificial intelligence. These technologies are crucial for both autonomous and semi-autonomous spacecraft. Robots equipped with advanced sensors can conduct scientific experiments on distant moons and planets, perform repairs, and gather data without risking human life. This automation enhances our ability to explore the most extreme environments across our solar system, providing critical information about areas we might eventually want to explore with humans. Additionally, advancements in materials science are paving the way for more resilient spacecraft. Lightweight, durable materials that can withstand the harsh conditions of space travel are essential. For instance, thermal protection systems made from advanced composites or heat-resistant ceramics can keep spacecraft intact during intense heat events like re-entry. This increased resilience not only improves the safety of missions, but also extends the lifespan of spacecraft in the field. Finally, the development of life support technologies is vital for long-duration missions beyond Earth. Innovations in recycling air and water, growing food in space, and managing waste will be crucial for missions to places like Mars. These technologies will ensure that astronauts can live and work on other planets for extended periods, fundamentally changing the way we think about space exploration and human presence in the cosmos. Every leap forward in these fields pushes the boundaries of what we can achieve, ushering in a new age of discovery. The quest for extraterrestrial life holds the potential to dramatically reshape our understanding of the cosmos in several fundamental ways. First, discovering even the simplest forms of life beyond Earth would challenge our assumptions about life's uniqueness. It suggests that the ingredients for life might be universal, increasing the likelihood that life exists throughout the universe. This realization would revolutionize our perspective, transforming how we conceive biological processes and evolution in a cosmic context. Second, understanding alien life forms could illuminate the conditions necessary for life to flourish. By studying environments on planets or moons where life could exist, such as Mars or the icy moon Europa, scientists might uncover new forms of biology that have adapted to conditions vastly different from our own. Insights gained from extraterrestrial ecosystems would encourage a broader definition of life, inspiring new research into extremophiles, organisms thriving in extreme conditions on Earth, and their potential counterparts elsewhere. Moreover, the pursuit of extraterrestrial intelligence invites profound philosophical questions about our place in the universe. It raises issues surrounding communication and interaction with intelligent species, and how these encounters, if they happen, might impact our culture, technology, and even our political structures. The potential revelation that we are not alone could unify humanity by shifting our focus away from terrestrial concerns towards a broader galactic perspective. Finally, exploring the vast cosmos in search of life forces us to advance our scientific and technological capabilities. The tools we develop for interstellar surveys, robotic spacecraft, and space exploration not only augment our ability to gather more data about the universe, but also push the boundaries of what is possible in science and engineering. As we unravel the mysteries of the cosmos, each discovery about potential life forms could lead us to new questions, igniting a continuous cycle of inquiry that deepens our understanding of the universe and our role within it. Among the many uncharted territories in our solar system, the icy moons of Jupiter and Saturn are considered some of the richest sources of potential discovery. Europa, one of Jupiter's moons, captivates scientists with its subsurface ocean, concealed beneath a thick layer of ice. This moon not only holds the possibility of harboring life, but also presents unique geological features such as ice plumes that could reveal signs of chemical processes similar to those on Earth. Researchers believe that Europa's ocean may be in contact with its rocky mantle, creating the right conditions for life as we know it. Enceladus, a small moon of Saturn, offers a similar allure. This moon has been observed ejecting geysers of water vapor and ice particles from its south pole, suggesting the presence of a subsurface ocean as well. The Cassini spacecraft discovered organic molecules in the plumes, making it a prime target for future exploration. The interplay of heat generated by tidal forces and the potential for hydrothermal vents on the ocean floor raises the tantalizing possibility that life might exist in these distant frozen worlds. Beyond the icy moons, the dwarf planet Pluto and its heart-shaped glacier known as Sputnik Planitia remain largely unexplored. The New Horizons mission, which passed by Pluto in 2015, revealed a complex landscape with mountains made of ice and possible geological activity. Scientists are eager to delve deeper into the geology and atmosphere of this distant world, which could help us understand the formation and evolution of similar bodies in the Kuiper Belt. Finally, The study of comets provides another realm for exciting discovery. These ancient cosmic wanderers are thought to contain primordial materials from the early solar system. Analyzing their composition can yield insights into the conditions that prevailed during the formation of the solar system and the origins of organic molecules that may have contributed to the emergence of life on Earth. The potential for breakthroughs in our understanding of life, the history of our solar system, and the universe at large lies in these unexplored frontiers. Advancements in artificial intelligence are poised to revolutionize the field of space exploration in numerous ways. One of the most significant contributions of artificial intelligence lies in its ability to process vast amounts of data at unprecedented speeds. Space missions generate enormous quantities of information, whether it is from telescopes observing distant galaxies or rovers analyzing the surface of other planets. Artificial intelligence can analyze this data, identify patterns, and make predictions, enabling scientists to draw insights that would be impossible for humans to discern alone. Artificial intelligence also enhances the autonomy of spacecraft and rovers. As missions venture further from Earth, real-time communication becomes more challenging due to the vast distances involved. Autonomous systems powered by artificial intelligence can make decisions based on local conditions without needing direct input from mission control. For example, if a rover on Mars encounters an unexpected obstacle, it can evaluate the situation and determine the best course of action, all while communicating data back to Earth for further analysis. Moreover, artificial intelligence can assist in the design and simulation of spacecraft. Utilizing machine learning algorithms, researchers can optimize various components of spacecraft to improve efficiency and durability. This can significantly reduce the time and costs associated with mission planning and manufacturing. Simulating different scenarios for real-world conditions allows scientists to predict how spacecraft will respond in the harsh environments of space, from extreme temperatures to radiation exposure. Finally, artificial intelligence can play a crucial role in the search for extraterrestrial life. By analyzing signals from space and processing data from planetary atmospheres, artificial intelligence can help identify potential biosignatures or chemical indicators of life. This leap forward offers the possibility of answering one of humanity's most profound questions: are we alone in the universe? As artificial intelligence continues to evolve, its applications in space exploration will undoubtedly expand, opening new frontiers in our understanding of the cosmos. Several future telescopes stand poised to transform our understanding of the universe as we delve deeper into its mysteries. One notable example is the James Webb Space Telescope, which launched at the end of 2021. With its advanced infrared capabilities, it aims to study the formation of stars and galaxies in the early universe. By observing celestial objects that emitted light billions of years ago, the James Webb Space Telescope promises to unveil insights about cosmic evolution that were previously inaccessible. Another ambitious project is the extremely large telescope currently being constructed in Chile, which will feature a mirror that is over 39 meters in diameter, making it one of the largest optical telescopes ever built. This powerful facility will enable astronomers to examine the atmospheres of exoplanets, investigate the nature of dark matter, and explore the formation of galaxies. Its high-resolution observations will provide an unprecedented view of the universe's intricacies. The Square Kilometre Array, a groundbreaking radio telescope project unfolding in Australia and South Africa, will consist of thousands of individual antennas working together as one enormous radio dish. Its primary goals include probing the origins of cosmic magnetism, studying the formation of the first stars, and gaining insights into the distribution of dark energy. This project could ultimately reshape our understanding of the universe's structure and evolution. Additionally, the European Space Agency's aerial mission will focus on characterizing the atmospheres of exoplanets through spectroscopy. By examining the chemical composition and weather patterns of these distant worlds, Ariel aims to enrich our comprehension of how planetary systems form and evolve. As these telescopes become operational, they will undoubtedly usher in a new era of cosmic discovery, revealing the universe's hidden depths and answering fundamental questions about our existence within it. Human exploration of Mars holds the potential to significantly enhance our understanding of planetary evolution. Mars presents a unique opportunity to study a planet that once exhibited conditions much like those on Earth. By sending astronauts to study its surface, collect samples, and conduct experiments, we can gather direct evidence regarding the geological history and climatic changes that have shaped the planet over billions of years. Through the analysis of Martian rocks and soil, scientists can determine the minerals present and their formation processes. This will provide insights into the volcanic activity that once occurred on Mars, as well as the water history that influenced its development. Understanding how Mars transitioned from a warmer, wetter environment to its current cold, arid state can reveal parallels with Earth's own evolutionary journey. This can lead to greater insight into the conditions necessary for life and how different planetary processes can lead to habitability or desolation. Furthermore, human exploration allows for real-time observation and experimentation. Astronauts equipped with advanced scientific instruments can investigate specific locations with greater precision than robotic missions. They could assess the impact of solar radiation on Martian regolith or search for potential biosignatures in ancient lake beds. These first-hand experiences could unlock mysteries that could remain unanswered through remote data alone. By comparing the geological and atmospheric data from Mars with that of Earth, scientists can test existing theories of planetary formation and evolution. This comparative approach could illuminate factors that influence climate, geological processes, and even the potential for life elsewhere in our solar system and beyond. Ultimately, the exploration of Mars could broaden our understanding of not just our neighboring planet, but the fundamental processes that govern the evolution of all rocky planets. Discoveries made by past space missions have profoundly shaped our understanding of the universe and continue to influence future explorations. For instance, missions like Voyager and Hubble have unveiled multitudes of cosmic phenomena, prompting scientists to reconsider the origins of the solar system and the potential for life beyond Earth. The information gathered, including details about the atmospheres of exoplanets and the geological features of Mars, serves as a foundation upon which new hypotheses are built. As we analyze the findings from these historic missions, we can identify specific targets and questions for future exploration. For example, the detection of water on Mars has led to increased interest in whether microbial life might exist beneath its surface. This has spurred missions aimed not just at planetary observation, but at sample collection and potential human exploration. Each new mission builds upon prior knowledge, allowing space agencies to make more informed decisions about where to direct their resources. The evolution of technology also plays a key role in leveraging past discoveries for future space missions. Innovations developed from early explorations have led to advancements in spacecraft design, imaging technology, and data analysis techniques. As we develop more advanced instruments to study the cosmos, we take the lessons learned from previous endeavors, adapting and refining our approach to meet the challenges of exploring distant worlds. Finally, the discoveries of past missions have fostered a collaborative spirit among countries and organizations around the globe. There is an increasing recognition that the pursuit of knowledge about the universe benefits from shared expertise and resources. As we look ahead, the cumulative insights gained from past explorations will not only guide our scientific inquiries, but will inspire a new generation of explorers eager to unravel the mysteries of the universe. Astrobiology is an interdisciplinary field that examines the origins, evolution, distribution, and future of life in the universe. By integrating insights from biology, chemistry, geology, and astronomy, scientists are making significant strides in understanding the potential for life beyond our planet. In recent years, the study of extremophiles, organisms that thrive in extreme environments on Earth, has reshaped our ideas about where life might exist elsewhere. These extraordinary creatures can survive conditions of intense heat, acidity, and radiation, suggesting that life could potentially endure in similar hostile environments on other celestial bodies. Moreover, missions to planets and moons within our solar system are bolstering our quest for extraterrestrial life. For instance, The exploration of Mars has revealed ancient riverbeds and minerals that imply the presence of liquid water in the past. The recent detection of organic compounds there fuels the notion that life could have existed. Additionally, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, are under scrutiny due to their subsurface oceans and the existence of necessary chemical ingredients for life. These discoveries directly inform astrobiologists about the conditions required for life and enable them to refine their search. The advent of powerful telescopes has also transformed our approach to astrobiology. With devices like the James Webb Space Telescope, scientists can analyze the atmospheres of exoplanets, planets orbiting stars beyond our solar system. Identifying key signatures of gases, such as oxygen and methane, provides insight into the potential for life on these distant worlds. The ability to detect biosignatures, indicators of biological processes, is a pivotal aspect of current research, expanding the possibilities of finding life beyond what we traditionally considered habitable zones. Finally, astrobiology raises profound philosophical questions about our place in the cosmos. Each discovery, whether it confirms or challenges the existence of life beyond Earth, influences our understanding of life's uniqueness and its potential diversity across the universe. The scientific pursuit of astrobiology not only enhances our knowledge of life as we know it, but also inspires humanity to consider the broader implications of life in the universe, igniting curiosity and fostering a deeper connection to the cosmos. Several promising missions are being planned to enhance our understanding of the outer solar system. One of the most exciting endeavors is the Europa Clipper mission, spearheaded by NASA. Set to launch in the early part of the next decade, this spacecraft will conduct detailed reconnaissance of Jupiter's moon Europa. Scientists are particularly interested in Europa due to its subsurface ocean, which may harbor the conditions necessary for life. The mission will assess the moon's ice shell thickness, survey its surface chemistry, and explore its potential habitability. Another intriguing mission is the Dragonfly project, also from NASA. Slated for launch in the mid-2020s, this innovative rotorcraft will land on Titan, Saturn's largest moon. Dragonfly aims to explore Titan's diverse chemistry and its liquid hydrocarbon lakes, searching for signs of prebiotic chemistry and perhaps even life. The concept of a flying drone allows for unprecedented mobility across the moon, enabling the examination of a variety of sites over its vast surface and providing a comprehensive survey of Titan's atmospheric and geological features. The European Space Agency is also contributing to our exploration of the outer solar system with the Jupiter Icy Moons Explorer, known as JUICE. Set to launch around the same time frame as the Europa Clipper, this mission will study Jupiter and its three largest icy moons, Ganymede, Callisto, and Europa. JUICE aims to uncover the icy shells of these moons and the oceans beneath, investigating the potential for life and understanding the processes shaping their evolution. These missions represent a significant leap in our efforts to explore the mysteries of the outer solar system. They will not only deepen our knowledge of celestial bodies that may hold clues about life beyond Earth, but also refine our understanding of planetary systems and their formation. As scientists collect more data from these distant worlds, we are likely to uncover new insights that could evoke transformative changes in our perspective on the cosmos. A deeper understanding of cosmic radiation could significantly influence the future of interstellar travel. Cosmic radiation consists of high-energy particles that originate from various astronomical sources, such as supernovae and black holes. These particles can pose serious health risks to astronauts, potentially leading to increased cancer rates and other long-term health issues due to their high penetrative power. By comprehensively studying cosmic radiation, scientists can develop better shielding techniques for spacecraft, ensuring the safety of crews on prolonged missions beyond our solar system. Additionally, an informed approach to cosmic radiation can aid in mission planning. Understanding radiation patterns and the environments of different regions in space allows researchers to identify safer trajectories. Some areas of space may have higher radiation levels due to galactic phenomena, while others could offer more protection. By navigating these zones carefully, Space missions can be optimized to minimize exposure, thereby enhancing the well-being of astronauts and the success of their objectives. Moreover, cosmic radiation could potentially be harnessed for energy. Advanced technology designs may incorporate systems that convert this radiation into usable energy, considerably improving spacecraft power supplies. This development could reduce reliance on traditional fuel sources, making long-duration interstellar missions more sustainable and viable. As humanity looks toward the stars, mitigating the effects of cosmic radiation and utilizing it to our advantage could open new frontiers in space exploration. Each discovery in this field pushes the boundaries of what we understand about the universe and our place within it, fueling the human spirit of exploration and innovation. Several major theories attempt to explain the origin of the universe, each offering a unique perspective on this profound question. The most widely accepted theory is the Big Bang theory, which posits that the universe began as an infinitely small and dense point approximately 13.8 billion years ago. This point then expanded rapidly, leading to the formation of matter, energy, galaxies, and all cosmic structures we observe today. Critical evidence, such as the cosmic microwave background radiation and the observable redshift of distant galaxies, supports this theory. Another alternative idea is the steady-state theory, which was more popular in the mid-20th century. This theory suggests that the universe is eternal and unchanging on a large scale, asserting that as it expands, new matter is continuously created to fill the gaps. While it provided a counterpoint to the Big Bang, the steady-state model has fallen out of favor due to lack of supporting evidence and observations that indicate an evolving universe. The cyclic model represents another interesting perspective. This theory proposes that the universe undergoes infinite cycles of expansion and contraction. After each Big Bang, the universe expands and then eventually collapses back into a singularity, leading to a new Big Bang. This idea raises questions about the nature of time and might provide insights into the behaviors we observe today. Finally, quantum theories and multiverse hypotheses introduce further complexity to the discussion. These suggest that what we perceive as our universe is just one of countless others, each with its own set of laws and constants. Quantum fluctuations could spark new universes in this multiverse. Each of these theories emphasizes different aspects of cosmic phenomena and invites ongoing exploration and debate as scientists seek to unravel the mysteries surrounding the origins of all existence. Scientists utilize computer simulations to build intricate models of the universe's evolution, allowing them to explore complex processes that are difficult to observe directly. These simulations can mimic the behavior of cosmic structures over vast timescales, from the formation of the first stars to the clustering of galaxies. By inputting known physical laws and initial conditions, researchers can recreate scenarios that illustrate how the universe evolves under various influences. One critical aspect of these simulations is their ability to account for gravity, dark matter, and dark energy. Gravity governs the attraction between masses and plays a significant role in the coalescing of matter into galaxies and clusters. Dark matter, although invisible, constitutes a significant portion of the universe's mass and affects the motion of visible matter. Dark energy, on the other hand, is the force thought to be driving the accelerating expansion of the universe. By incorporating these elements into simulations, scientists can scrutinize how the universe evolves from a hot, dense state to its current, largely cold and empty expanse. Computer simulations also allow scientists to test different theories about the universe's formation and behavior. They can explore different models of cosmic inflation or the behavior of dark energy to see how their predictions match observational data. For example, when comparing simulation outputs to actual cosmic maps generated by telescopes, researchers can refine their understanding of the universe's structure and refine their models accordingly. This iterative process helps astrophysicists understand discrepancies and prompt new lines of inquiry. As technology advances, simulations continue to improve in fidelity and accuracy, giving scientists even greater insights into cosmic evolution. They are now able to simulate billions of particles across millions of light-years, effectively capturing the complexity of reality. The results from these simulations not only deepen our understanding of the universe's past, but also help predict its future, shedding light on scenarios that may unfold billions of years from now. The quest to unite general relativity with quantum mechanics has been a long-standing challenge in modern physics. General relativity describes gravity as the curvature of spacetime caused by mass and energy, while quantum mechanics handles the behavior of particles on the smallest scales. The disparity between these two foundational theories leads to puzzling scenarios, particularly in extreme conditions like the centers of black holes or the moments after the Big Bang. Theories of quantum gravity aim to bridge this divide by developing a framework that accommodates both the smooth, continuous nature of spacetime described by general relativity and the discrete, probabilistic nature of the quantum world. One prominent approach is string theory, which posits that the fundamental building blocks of the universe are not point particles, but rather tiny, vibrating strings. These strings can exist in multiple dimensions, with the different vibrational modes corresponding to various particles. This framework tends to naturally incorporate gravitational effects while also aligning with the principles of quantum mechanics. Another approach is loop quantum gravity, which focuses on quantizing spacetime itself. In this theory, spacetime is described as a network of interconnected loops, which suggests that at the smallest scales, space is not continuous but rather granular. Loop quantum gravity preserves the predictions of general relativity at larger scales, while introducing quantum mechanics directly into the structure of spacetime. This innovative perspective allows for the possibility of a finite, discrete universe and aims to resolve issues like the singularities found in black holes. The journey to a comprehensive theory of quantum gravity continues to inspire physicists. As research progresses, the hope is that a successful unification will not only resolve fundamental conflicts, but also deepen our understanding of the universe, potentially revealing new phenomena beyond our current grasp. The implications of such a discovery could redefine our concept of reality and our place within the cosmos. String theory reshapes our understanding of fundamental forces by proposing that the basic building blocks of the universe are not point-like particles, but instead tiny vibrating strings. The length scale of these strings is incredibly small, about the size of the Planck length, which is far beyond the reach of our current experimental capabilities. Each vibration mode of these strings corresponds to a different particle, including those that make up the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. One remarkable implication of string theory is its potential to unify all fundamental forces under a single theoretical framework. Traditional physics has treated gravity and quantum mechanics as separate domains, leading to inconsistencies when trying to explain phenomena at the quantum level, particularly near black holes or during the early moments of the universe. String theory offers a common underpinning that could resolve these discrepancies by illustrating how all forces emerge from different string vibrations. Moreover, string theory introduces extra dimensions beyond the familiar three of space and one of time. While we experience the world in 4 dimensions, string theory suggests there may be additional dimensions, potentially 6 or 7, that are compactified or curled up in ways that are not visible at everyday scales. These extra dimensions could play a crucial role in understanding how forces interact and lead to the variations in particle mass and charge observed in nature. The exploration of string theory also carries implications for our concepts of reality and the universe. It has sparked conversations about the fundamental nature of time, space, and matter. By providing a framework for unifying forces and suggesting hidden dimensions, string theory continues to push the boundaries of theoretical physics, inspiring new research and prompting questions about the very fabric of our universe. This pursuit into the nature of reality could redefine our comprehension of the forces that govern everything from the smallest particles to the vast cosmos. New findings in cosmology continually shape our understanding of the Big Bang theory. which posits that our universe began from an incredibly hot and dense state around 13.8 billion years ago. For instance, recent observations from advanced telescopes have allowed scientists to gather more data on the cosmic microwave background radiation, a faint glow left over from the Big Bang. This radiation carries crucial information about the early universe's conditions and supports many aspects of the Big Bang theory. However, as scientists delve deeper into the cosmos, they encounter phenomena that challenge existing models. Discoveries like the unexpected behavior of certain galaxies or the distribution of dark matter raise questions about how accurately the Big Bang theory describes the universe's evolution. For instance, the discovery of galaxies forming earlier than predicted can provoke a re-evaluation of theories related to cosmic inflation, the rapid expansion of the universe shortly after the Big Bang. These findings may either refine the current theory or force scientists to develop new models. In addition, emerging theories such as those involving quantum gravity challenge traditional interpretations of the Big Bang. Concepts from these theories suggest potential scenarios where the universe could recycle itself through cycles of expansion and contraction, deviating from a singular initial explosion. As researchers explore these ideas, they push the boundaries of our understanding, indicating that the Big Bang may not be the only narrative about the universe's origins. The interplay between supportive evidence and challenging observations creates a dynamic landscape in cosmology. With every new discovery, we inch closer to a more comprehensive picture, revealing that our understanding of the universe is never static, but instead continuously evolving, shaped by the relentless quest for knowledge in the field of astrophysics. Some cosmologists are investigating alternative cosmological models like cyclic universes due to the limitations and unanswered questions arising from the traditional Big Bang theory. While the Big Bang model has been incredibly successful in explaining many aspects of our universe, certain phenomena, such as the accelerating expansion of the cosmos and the nature of dark energy, prompt scientists to consider other frameworks. These unexplained features of our universe suggest that our current understanding may not provide the full picture. Cyclic universe models present an intriguing alternative. In these theories, the universe undergoes a series of expansions and contractions, with each cycle resetting the conditions of the universe. This idea challenges the notion of a singular beginning to the universe and proposes that cosmic evolution is an endless process. Moreover, cyclic models offer potential explanations for cosmic phenomena that have remained enigmatic, including the uniformity of the cosmic microwave background radiation and the distribution of galaxies. Exploring these alternative models can help address fundamental questions about the origin, structure, and ultimate fate of the universe. For instance, if the universe is indeed cyclical, it raises new discussions about entropy, the second law of thermodynamics, and the implications for our understanding of time itself. As researchers delve into these subjects, they seek a comprehensive understanding that could unify various aspects of cosmology, providing insights into everything from the very small scales of quantum mechanics to the vastness of cosmic structures. The diversity of thought in cosmological models reflects scientists' desire to push the boundaries of knowledge. By evaluating these alternative theories, cosmologists not only enrich the scientific discourse, but also open doors to new avenues of research that may fundamentally alter our perception of the universe and our place within it. This exploration underscores the dynamic nature of science, wherein the pursuit of knowledge often leads to more profound questions and unexpected discoveries. Researchers tackle the challenge of predicting future cosmic events through a combination of observational data, mathematical models, and simulations. By studying the patterns and behaviors of celestial bodies and phenomena, they aim to understand the underlying principles that govern the universe. For example, the motion of planets can be predicted with remarkable accuracy by employing Kepler's laws of planetary motion. These laws describe how celestial objects move in orbits and provide a framework for anticipating their future positions. The use of advanced telescopes and other technology allows astronomers to gather vast amounts of data from different regions of the universe. This data includes observations of stars, galaxies, and even distant supernovae. By collecting and analyzing this information, researchers can develop a clearer picture of various cosmic events, such as the life cycles of stars, the behavior of black holes, and the formation of galaxies. Mathematical modeling plays a crucial role as well. Scientists create equations that approximate the complex interactions between cosmic entities. These models can be enhanced using supercomputers, which allow for intricate simulations of cosmic events over large timescales. For instance, simulations can illustrate how galaxies evolve and merge, giving insights into future configurations that may arise. Researchers also rely on the principles of probability and statistics to account for uncertainties in their predictions. Cosmic events can be influenced by numerous factors, and some variables remain difficult to measure. By assessing probabilities and modeling various scenarios, scientists can provide more robust predictions regarding events such as asteroid impacts or the likelihood of supernova explosions. This multifaceted approach continues to enhance our understanding and predictability within the cosmos. Although scientists have made tremendous strides in understanding the universe's evolution, the initial conditions that sparked the cosmos are still shrouded in mystery. One of the most pressing questions is what exactly occurred during the moment known as the Big Bang. This event marks the beginning of time and space as we know them, but the specifics of what caused it and what the state of the universe was at that moment remain elusive. Theories suggest that before the Big Bang, all the energy and matter of the universe may have been concentrated in an infinitely dense and hot point, often referred to as a singularity. However, the laws of physics as we currently understand them break down under such extreme conditions. This creates a significant gap in our comprehension of the earliest moments of existence. Research into quantum gravity and string theory aims to bridge this gap, potentially revealing insights into how space and time emerged. Another critical area for exploration involves cosmic inflation. This theory proposes that the universe underwent a rapid expansion just fractions of a second after the Big Bang, leading to the large-scale structure we observe today. Understanding the mechanisms behind this inflationary period could clarify much about the initial conditions. Scientists are eager to identify the physical processes and forces at play during inflation, including whether an inflationary field existed and how it may have interacted with other components of the early universe. Additionally, investigations into the cosmic microwave background radiation provide a snapshot of the universe just 380,000 years after its birth. However, these observations only paint a partial picture of the very first moments. To gain deeper insights, researchers utilize particle accelerators and large telescopes, continually seeking more precise measurements and new data that might unravel the secrets of our universe's origins. The continued pursuit of answers in this field is crucial, as it drives forward our understanding of not just where the universe came from, but also the fundamental nature of reality itself. Scientists reconcile observational data with theoretical models of the cosmos through a dynamic interplay between experimentation, observation, and adjustment of existing theories. The process begins with the development of cosmological models based on established scientific principles and laws such as general relativity. Once these models are formulated, astronomers and physicists collect observational data using advanced technology, including telescopes that span across multiple wavelengths of light, like radio, infrared, and visible. When new observations are made, scientists scrutinize how well their theoretical models explain these findings. If the observational data aligns closely with predictions, it supports the validity of the model. However, when discrepancies arise, researchers are prompted to examine their assumptions, refine their theories, or even develop entirely new models. This iterative approach ensures that the understanding of the cosmos evolves with the accumulation of fresh data, leading to richer insights. An intriguing aspect of this reconciliation lies in how scientists use statistical methods to weigh the evidence. For instance, they might conduct simulations based on a model and then compare the simulated results with real observations. If a model consistently fails to account for significant phenomena, such as the accelerating expansion of the universe, it indicates that either new physics or modifications to the model are necessary. Moreover, collaboration among scientists from various disciplines enhances the reconciliation process. Physicists, astronomers, cosmologists, and even computer scientists work together, integrating findings across different fields to create a more comprehensive view of the universe. This collaborative environment encourages a continual re-evaluation of theories based on observational evidence, leading to a deeper understanding of the cosmos and our place within it. Interdisciplinary research serves as a crucial catalyst for advancing cosmological theories by fostering collaboration among diverse fields of study. Cosmology, the scientific study of the universe's origin, evolution, and ultimate fate, draws on insights from physics, astronomy, mathematics, and even philosophy. By integrating methodologies and perspectives from these disciplines, researchers can build a more comprehensive understanding of complex cosmic phenomena. For instance, advancements in theoretical physics, particularly in areas such as quantum mechanics and general relativity, have significantly impacted interpretations of the early universe. Collaborations between particle physicists and cosmologists have led to groundbreaking theories, like the possibility of cosmic inflation, which describes an exponential expansion of space in the moments following the Big Bang. This synergy between disciplines allows for the testing and refining of ideas, promoting a more robust scientific framework. Additionally, data from observatories equipped with cutting-edge technology often requires expertise in engineering, computer science, and even data analytics to be properly interpreted. When astronomers partner with these experts, they can develop sophisticated algorithms and tools that unveil patterns hidden within vast amounts of cosmic data. This multidimensional approach not only enhances our understanding of the universe, but also drives innovation in these contributing fields. Interdisciplinary research not only enriches our comprehension of cosmological concepts, but also opens new avenues of inquiry. By fostering connections between seemingly unrelated fields, exciting discoveries emerge, stimulating fresh questions and ideas. As we continue to explore and understand the universe, this collaborative spirit is essential in unraveling the intricate tapestry of cosmic history. Cultural beliefs play a significant role in shaping humanity's understanding of the universe, often serving as lenses through which people interpret celestial phenomena and the nature of existence. Throughout history, different cultures have developed their own mythologies, cosmologies, and philosophical frameworks to explain the cosmos. For example, ancient civilizations such as the Greeks and Babylonians crafted narratives that associated gods and goddesses with planetary bodies, reflecting their cultural values and experiences. The impact of these beliefs extends into the present day. Contemporary cultures continue to view the universe through specific value systems and traditions. For instance, some indigenous cultures may view the cosmos as a living entity, emphasizing a relationship with nature and the universe that is reciprocal rather than hierarchical. This holistic perspective often influences practices relating to astronomy, agriculture, and environmental stewardship. Moreover, the way scientific advancements are received can be heavily influenced by cultural interpretations. In societies where scientific reasoning is widely accepted, there is often a stronger connection to advances in understanding the universe, such as the Big Bang theory or the concept of black holes. Conversely, in cultures where traditional beliefs hold sway, there may be resistance to ideas that challenge established narratives, even in the face of overwhelming evidence. The interplay between cultural beliefs and scientific understanding is ongoing, perpetually shaping humanity's quest for knowledge about the universe. As global communication increases and diverse perspectives intermingle, our collective understanding continues to evolve, revealing both the wonders of the cosmos and the profound impact of cultural narratives on our perceptions. Space exploration profoundly influences society's understanding of humanity's role within the universe. Over the years, missions to the Moon, Mars, and beyond have expanded our knowledge and sparked a sense of wonder about our planetary neighborhood and the vast expanse beyond. Images taken from space, such as the iconic Earthrise photograph, have shifted perspectives, reminding us of our planet's fragility and the interconnectedness of life on Earth. These moments often inspire citizens to reflect on their existence and our shared responsibility to protect our home. As we delve deeper into space, new discoveries challenge and refine our place in the cosmic narrative. The search for extraterrestrial life, for example, raises fundamental questions about whether we are alone in the universe. Discoveries of exoplanets in habitable zones around distant stars suggest possibilities for life beyond Earth. This pursuit ignites curiosity and discussion, pushing us to consider how our lives fit into the broader tapestry of existence and what implications such findings could have for humanity's future. Moreover, space exploration acts as a unifying force, transcending national boundaries and fostering global collaboration. International efforts, such as the International Space Station, highlight our shared goals and aspirations, framing our endeavors not just as scientific missions but as crucial steps in human achievement. This cooperation brings different cultures together, generating a collective identity as humans navigating the cosmos together. Through advancements in technology and a growing body of scientific knowledge, the exploration of space continues to reshape societal perceptions. Each mission not only enhances our understanding of the universe, but also captures the imagination of people worldwide. This ongoing journey into space fuels dreams and ambitions, encouraging generations to look up and ponder their place in an ever-expanding universe filled with mystery and potential. Educational initiatives play a crucial role in enhancing public awareness about cosmic mysteries by making complex concepts accessible and engaging. These programs often take the form of workshops, lectures, and interactive exhibits at science centers and planetariums. Through engaging presentations, educational organizations aim to ignite curiosity and inspire a sense of wonder about the universe, addressing topics like black holes, dark matter, and the origins of the cosmos in approachable ways. Schools and universities are also key players in this effort. Many institutions integrate astronomy and cosmology into their curricula, providing students with hands-on experiences through telescopes, simulations, and collaborative projects. By fostering a learning environment that encourages inquiry and exploration, educators are equipping a new generation with the tools to understand and appreciate the vastness of space and the exciting mysteries it holds. Additionally, initiatives supported by public outreach through social media and online platforms are becoming increasingly popular. These digital resources allow experts to share their knowledge and findings with a global audience, democratizing access to scientific information. People can engage with thought-provoking content such as interviews, documentaries, and live-streamed lectures, sparking discussions and generating interest in cosmic phenomena. Moreover, community events such as science fairs, star parties, and astronomy clubs foster a sense of collective exploration. These gatherings bring individuals together to share experiences and findings, deepening public engagement with the universe. By combining education with collaboration, these initiatives not only raise awareness, but also create a shared appreciation for the cosmic mysteries that continue to captivate human curiosity. Public engagement plays a crucial role in advancing space research and exploration by fostering awareness, interest, and support for scientific endeavors. When members of the public are informed and involved, they become advocates for funding and policy making that prioritize space initiatives. Engaging the public boosts enthusiasm for science and encourages the next generation to consider careers in technology, engineering, and space sciences. These fields require bright minds, and a passionate public can stimulate that interest early on through education and outreach programs. Moreover, public engagement allows scientists to communicate their findings and objectives effectively. When researchers share their discoveries and the significance of their work, it can transform how people perceive space exploration. Stories about distant planets, asteroid missions, and the search for extraterrestrial life capture the imagination and can lead to increased support for ambitious projects, like sending humans to Mars or establishing a permanent presence on the Moon. Public fascination can translate into tangible aid for organizations like NASA and private companies working on cutting-edge space technology. Another important aspect is that listening to the public's perspective can enhance the direction of research. Different communities have unique interests and concerns regarding space exploration, from planetary defense to the ethics of space colonization. Through engagement, researchers can gather valuable insights and create programs that reflect public priorities and values, making space exploration a shared journey rather than a segregated endeavor. Public engagement also serves to demystify science. By fostering open communication between scientists and the general populace, misconceptions can be addressed and trust can be built. As people gain a better understanding of scientific processes, they are more likely to support policies that promote space exploration. The more the public is involved, the more they contribute to a culture that values scientific inquiry, ultimately propelling humanity further into the cosmos. The portrayal of space in media and literature has significantly shaped public interest in astronomy over the years. Books, movies, and television shows have captured audiences' imaginations, often blending scientific concepts with human drama and adventure. Works like Jules Verne's From the Earth to the Moon and more recent films like Interstellar and The Martian have not only entertained, but have also sparked curiosity about the cosmos. This intersection of storytelling and science has made complex astronomical ideas more approachable and exciting. For many, these portrayals create a sense of wonder about the universe. When characters embark on journeys to distant planets or confront the mysteries of black holes, viewers are invited to think beyond Earth. This often leads to a desire for deeper knowledge regarding space exploration, astrobiology, and even theoretical physics. As stories highlight themes of exploration and the search for life beyond our planet, they encourage audiences to seek out real scientific information about these topics, resulting in increased interest in astronomy. Furthermore, educational programs and documentaries featuring engaging visuals and compelling narratives spark interest in a broad audience. Channels that provide ongoing coverage of astronomical events, such as solar eclipses or planetary alignments, often see spikes in viewership and public engagement. Events like these, coupled with media portrayals, foster a culture of curiosity where people feel compelled to look up at the stars and wonder about their significance. As public interest grows, so does funding for scientific research and educational initiatives in astronomy. Popular portrayals often influence the next generation of scientists and astronomers, inspiring children to gaze through telescopes and pursue careers in space exploration. Ultimately, the impact of media and literature on public engagement with astronomy is profound, serving as a bridge between imagination and scientific reality. Citizen science serves as a powerful tool in expanding our understanding of the universe by harnessing the enthusiasm and skills of everyday individuals. People from various backgrounds can contribute to scientific research, aiding professionals in gathering data, monitoring celestial events, and even analyzing vast amounts of information that would otherwise be overwhelming for a small number of scientists alone. This collaborative approach can lead to groundbreaking discoveries and accelerate research in cosmology and other scientific fields. One notable example is the involvement of amateur astronomers in the observation of astronomical phenomena. With the advent of affordable telescopes and accessible software, these enthusiasts can track the movements of asteroids, comets, and variable stars, providing vital data to professional scientists. Their findings can sometimes lead to significant discoveries, such as identifying new celestial bodies or contributing to the study of light curves, which reveal information about distant stars and galaxies. Furthermore, citizen science projects, such as Galaxy Zoo, invite volunteers to classify millions of galaxy images. The collective efforts of participants have resulted in discoveries of unexpected galaxy shapes and formations that challenge existing theories. This phenomenon occurs because human observers can often spot patterns or anomalies that algorithms might overlook. The contributions from these diverse participants often yield insights that enhance our understanding of the structure and evolution of the universe. Finally, citizen science extends into the realm of theoretical research as well. Individuals can simulate cosmic events or participate in the analysis of data from projects like the Laser Interferometer Gravitational Wave Observatory. By engaging a broader community in these scientific endeavors, we not only increase the available intellectual resources, but also inspire a deeper public interest in science and astronomy. The result is a richer, more nuanced comprehension of the cosmos and our place within it. Celestial phenomena have captivated human imagination across cultures for centuries, with different societies interpreting these events through the lenses of their own beliefs and traditions. For instance, ancient civilizations like the Babylonians meticulously recorded planetary movements, viewing them as omens that could dictate the outcomes of battles and the prosperity of harvests. They believed that the alignment of stars and planets was closely tied to divine authority, shaping their understanding of fate and fortune. In contrast, indigenous cultures often view celestial phenomena as a means to connect with their ancestors and the natural world. The Inuit, for example, associated the northern lights with the spirits of their ancestors dancing in the sky. Their interpretations were not just myths, but integral to their identity, influencing their navigation, storytelling, and seasonal ceremonies. Each cultural perspective provides insight into how people relate to the universe, finding meaning and connection in the movements of stars and celestial bodies. Additionally, Asian cultures have their own distinctive interpretations. In Chinese astronomy, the movement of celestial bodies was linked to the moral conduct of rulers. The appearance of unusual events like comets was often seen as a warning sign that could lead to significant changes in leadership. This interplay between celestial events and societal well-being showcases how cultures translate the cosmos into guidance for their own lives and decisions. The varying interpretations of celestial phenomena reflect not only a diversity of beliefs, but also a common human experience. They reveal a connection to the universe that transcends cultural differences, indicating our shared longing to understand our place within it. Through these interpretations, we can appreciate how deeply intertwined humanity is with the cosmos, reminding us that celestial events, whether viewed as omens, ancestral connections, or moral indicators, continue to fascinate and inspire across time and space. The search for extraterrestrial intelligence, often abbreviated as SETI, serves as a fascinating reflection of humanity's deepest desires and fears. At its core, this quest embodies our longing for connection beyond our planet, the hope that we are not alone in the universe. This desire is driven by a mix of curiosity and existential contemplation. Throughout history, humans have gazed at the night sky, pondering the nature of the cosmos and our place within it. The potential discovery of intelligent life offers not just validation of our existence, but also the possibility of sharing knowledge and experiences with beings from other worlds. Yet, this search simultaneously taps into profound fears. The implications of contacting extraterrestrial civilizations stir apprehensions about our safety, ethics, and the very nature of humanity. Many wonder about the intentions of these beings. Will they be benevolent, indifferent, or hostile? Science fiction often explores these fears, presenting scenarios where contact leads to either uplifting collaboration or catastrophic consequences. Such narratives can provoke anxiety about our vulnerabilities as a species and our capacity to handle the unknown. Additionally, this effort reflects our underlying fears of isolation and insignificance. Discovering that intelligent life exists elsewhere might challenge our self-importance, highlighting how small and fragile our existence is in the vast cosmos. This realization can trigger a fear of being just one of many civilizations, perhaps even one that is not particularly special. It raises questions about the sustainability of life and whether civilizations rise and fall, echoing a sense of impermanence. The scientific pursuit of extraterrestrial intelligence also mirrors our drive to understand the nature of life itself. By asking whether life exists elsewhere, we are simultaneously exploring what it means to be alive and how we define intelligence. This investigation inspires both hope for technological and cultural advancements through contact, as well as concern over our existential questions. The delicate balance between these desires and fears fuels an ongoing conversation that invites us to reflect on our identities, our ambitions, and the potential of the universe around us. Interdisciplinary collaborations play a vital role in expanding our understanding of the cosmos. By bringing together experts from various fields such as physics, astronomy, biology, and even philosophy, These partnerships create a rich environment where diverse perspectives contribute to a deeper comprehension of complex phenomena. For instance, astrophysics benefits significantly from insights in mathematics and computer science, which help in modeling cosmic events and simulating galaxy formations. The integration of different scientific perspectives often leads to innovative solutions to long-standing questions. An example of this is the collaboration between astronomers and chemists, which has unveiled the intricate chemical processes occurring in stellar environments. Understanding the composition of stars and the formation of molecules in space not only enhances our knowledge of the universe, but also has practical implications for fields like astrobiology, where knowledge of potential life-sustaining compounds is crucial. Furthermore, interdisciplinary work tends to challenge conventional paradigms, encouraging scientists to think outside of established boundaries. This has driven groundbreaking research, such as investigating the potential for life on other planets by combining insights from geology, biology, and atmospheric science. Each discipline introduces unique methodologies and ideas, fostering creativity and paving the way for unexpected discoveries. As technological advancements continue to unfold, these collaborations become even more essential. The development of sophisticated instruments, such as powerful telescopes and advanced data analysis software, requires a blend of expertise, ensuring that we not only gather vast amounts of data, but also interpret it effectively. All of this underscores how collaborative efforts across various fields act as a catalyst for advancing cosmic knowledge, allowing humanity to explore and understand the universe more comprehensively than ever before. The potential discovery of extraterrestrial life introduces a host of ethical considerations. One of the foremost concerns is whether we have the right to intervene in or explore the environments inhabited by these life forms. Many scientists and ethicists argue that we must protect other ecosystems from the damaging effects of human exploration, similar to the conservation efforts we undertake on Earth. Just as we strive to preserve endangered species and delicate habitats on our planet, the same principles might extend to extraterrestrial realms. Another significant ethical consideration involves the rights of extraterrestrial beings. If these life forms are found to possess intelligence or complex social structures, it raises profound questions about their autonomy and the moral obligations humanity might have towards them. Would we have a responsibility to communicate with them, share knowledge, or even ensure their survival? The implications challenge our traditional notions of life and rights, forcing us to reconsider how we define sentient beings. Furthermore, the potential impact on humanity's worldview cannot be overlooked. The discovery of intelligent extraterrestrial life could alter our understanding of our own place in the universe, leading to philosophical and cultural shifts. This could catalyze global unity in sharing knowledge and resources, or conversely, it might incite fear and conflict over the new presence in our cosmic neighborhood. The reactions could vary greatly, detailing how we collectively treat such findings and the narratives we construct around them. The technological and scientific methods we employ in seeking extraterrestrial life must also be examined. There is concern over contamination, both in terms of Earth organisms affecting alien ecosystems and the reverse. The protocols that govern space exploration must reflect a deep consideration of ethical responsibility, ensuring that our pursuits do not inflict irreversible damage to potential extraterrestrial habitats. The balance between scientific discovery and moral obligation is crucial as humanity continues to reach for the stars. Every new discovery in the realm of cosmology has the potential to significantly shift our understanding of the universe, reshaping established paradigms and prompting us to reconsider what we know. When we learn about a new celestial phenomenon or a different aspect of physics, it often reveals complexities and relationships that challenge earlier conceptions. For instance, the detection of gravitational waves in 2015 not only confirmed a prediction of Albert Einstein's theory of general relativity, but also opened a new avenue for observing the universe, dubbed gravitational wave astronomy. The discovery of dark energy has similarly transformed our comprehension of cosmic expansion. Initially, scientists viewed the universe as slowing down in its expansion due to gravitational forces. However, when evidence emerged suggesting that this expansion is accelerating, it forced a re-evaluation of cosmic forces at play. This phenomenon, attributed to dark energy, suggests that our understanding of the fabric of the universe is much more intricate than previously thought, leading to numerous theories and ongoing investigations. Moreover, advancements in technology, such as more powerful telescopes and sophisticated data analysis techniques, allow astronomers to gather increasingly detailed information about distant galaxies, black holes, and exoplanets. Each significant finding often leads to more questions than answers. For example, the discovery of potentially habitable exoplanets raises critical questions about the conditions required for life and leads scientists to explore the nature of habitability beyond our own solar system. As these discoveries accumulate, they weave a richer tapestry of cosmic knowledge, compelling researchers to engage in interdisciplinary studies that blend physics, astronomy, and even philosophy. The dynamic nature of scientific inquiry means that with each breakthrough, our cosmic narrative evolves, encouraging a continuous quest for knowledge and a deeper understanding of our place in the universe. Numerous challenges persist in the quest to unlock deeper cosmic mysteries, presenting obstacles that researchers and scientists are eager to overcome. One significant challenge is the enigmatic nature of dark matter and dark energy, which together constitute approximately 95% of the total mass energy content of the universe. Knowing that we only observe a small fraction of the universe through conventional means truly underscores the complexity of this issue. Efforts are underway to understand these phenomena, yet our inability to directly observe them complicates our understanding and hinders progress in cosmology. Another critical hurdle is the advancement of observational technology. Telescopes, both ground-based and space-based, are vital tools that enable us to explore the cosmos. However, existing telescopes face limitations in sensitivity and resolution. Future observatories must strive for enhanced capabilities to detect faint signals and detail distant celestial objects. Innovations in technology will also support the exploration of high-energy cosmic events that could provide vital clues about the universe's evolution and fundamental laws of physics. The development of a unified theory of physics remains one of the most profound challenges. General relativity, which describes gravity, and quantum mechanics, which addresses the behavior of subatomic particles, currently operate in separate realms of understanding. Merging these two frameworks into a cohesive theory remains an elusive goal. Achieving this could revolutionize our comprehension of not only the cosmos, but also the very nature of reality itself. Additionally, the need for international collaboration is crucial when addressing these cosmic challenges. The complexity of the universe necessitates shared knowledge, resources, and expertise across borders. When scientists from diverse backgrounds unite, they foster innovation and forge pathways to breakthroughs that can be transformative. By embracing this collaborative spirit, humanity can venture further into the depths of the universe, unlocking secrets that have long eluded our grasp. The quest to understand the universe has always ignited curiosity and imagination, serving as a beacon for future generations of scientists and thinkers. Today's discoveries, from the vast expanse of dark matter to the intricate dance of celestial bodies, symbolize the profound interconnectedness of everything in existence. This pursuit fosters critical thinking and problem-solving skills, as young minds are encouraged to ask questions and seek answers about the nature of reality. As students explore concepts such as quantum mechanics and relativity, they are not merely learning facts, they are participating in a dialogue that spans generations. The stories of legendary scientists like Albert Einstein, Marie Curie, and Carl Sagan can motivate young individuals to envision their own potential contributions to the field. When they recognize that the universe is dynamic and full of mysteries waiting to be unraveled, it can cultivate a passion that drives them toward careers in science, technology, engineering, and mathematics. Moreover, initiatives in science communication alongside hands-on programs in observatories and laboratories make these complex ideas more accessible. By aligning the awe of cosmic phenomena with practical experience, budding scientists see the tangible impact their work might have on our understanding of the universe. Engaging demonstrations, interactive experiments, and even virtual reality simulations can transport students to the depths of space, providing a visceral understanding of concepts that often feel abstract. Ultimately, the pursuit of cosmic knowledge transforms the way we view our place in the universe. As future scientists grapple with questions that stretch the boundaries of human understanding, this journey not only shapes their intellect, but also instills a sense of wonder and responsibility toward the world they inhabit. Empowered by this knowledge, they will be more equipped to address the challenges humanity faces, potentially leading to groundbreaking innovations inspired by the universe's mysteries. Collaboration among international space agencies is crucial for advancing cosmic research, as it allows countries to pool their resources, expertise, and technology in pursuit of common goals. Space exploration presents immense challenges that often exceed the capabilities of any single nation. By working together, agencies like NASA, the European Space Agency, and Roscosmos can share costs and enhance scientific output. For instance, projects like the International Space Station exemplify this collaborative spirit, serving as a platform where scientists from various countries conduct experiments that benefit all of humanity. The sharing of data and discoveries across borders accelerates the pace of research. When space agencies collaborate, they can combine different types of instruments and observational data, leading to more comprehensive studies of phenomena like black holes, dark matter, and cosmic radiation. This cooperation has facilitated groundbreaking missions such as the Hubble Space Telescope, which has provided invaluable insights into the universe, thanks to a collective effort from numerous countries and scientists. Moreover, collaboration fosters innovation. When diverse teams from different nations work together, they bring unique perspectives and approaches to problem solving. This cross-pollination of ideas often leads to technological advancements that can be applied not just in space exploration, but also in other fields, such as medicine and disaster response, showcasing the broader impact of scientific cooperation. Finally, international collaboration in space fosters peaceful relations among countries. As nations come together in pursuit of knowledge, they build trust and understanding while demonstrating a collective commitment to addressing challenges that affect the entire planet, such as climate change and potential asteroid threats. In a time when global cooperation is more critical than ever, the collaboration among space agencies stands as a powerful testament to what humanity can achieve when united in the spirit of discovery. As humanity's quest for understanding the universe deepens, our relationship with the cosmos is likely to undergo a profound transformation. With every discovery, whether it be the detection of exoplanets or the identification of cosmic phenomena like black holes, we start to unravel the mysteries that surround us. This expanding knowledge not only satiates our curiosity, but also intertwines our existence more deeply with the universe, making us acutely aware of our place within it. The progression of technology plays a pivotal role in shaping this future. Advances in telescopes and space exploration vehicles enable us to see farther into the universe than ever before. These breakthroughs may lead to new forms of communication and potential collaboration with other advanced civilizations, should they exist. The idea of a universal community, connected by the shared experience of existence, begins to take on tangible possibilities, with the potential for learning from the experiences of others beyond our planet. Moreover, as we continue to probe the intricacies of dark matter and dark energy, our understanding of the fundamental forces that shape the universe may influence philosophical and ethical implications for humanity. Questions about life's purpose, the sustainability of our planet, and the future of human evolution could lead to new paradigms in how we view ourselves. We might become more unified in our endeavors, recognizing the importance of stewardship of both Earth and space as we reach for the stars. Finally, our expanding knowledge could enable us to harness cosmic resources, from asteroid mining to harnessing energy from the sun, which may transform our societies. The concept of venturing beyond Earth might evolve into a normalized aspect of human life, leading to communities on other planets or moons, broadening our scope of existence. This potential journey holds the promise of not just survival, but of flourishing as an interstellar species and redefining what it means to be human in an ever-expanding universe.